to using traditional living shoreline techniques. And those are very high wave energy environments like the ocean coast. From an engineering perspective, when a guaranteed level of protection is required, for example, if I have critical infrastructure like a fire department or a hospital, I am most likely going to want to protect that with a seawall or something that can guarantee a level of protection so that that facility can operate under the extreme circumstances that it's required to serve the public. Another important challenge to consider, and this is probably going to be one of the most oftenly faced challenges with living shorelines, is very steep banks. In order to dissipate wave energy over a wide area, you oftentimes need to regrade the shoreline and the upland bank area. And looking at this picture from Lake Erie, you can see we have enormous houses very close to a very steep bank. There's just not enough room to regrade this to dissipate energy over a wide area. And so that's why you see a lot of stone being used for shoreline protection in this area. A living shoreline is probably not going to be possible in this case. So I think of site evaluation being on the spectrum that includes concept design, full engineering design, and construction. The information that you're going to be gathering using our guidance and worksheet during site evaluation will naturally inform your concept design. You'll start to think, oh, if I see this parameter, I might want to choose this technique, or I might see higher wave energy, so I'm definitely not going to put this out there. And there's some feedback there. As soon as you start conceptualizing your design, you might realize you want to look at certain other things while you're in the field. So there's a continuity between site evaluation up to construction, where a lot of the information is going to be passed from one step to the other. So if we think of site evaluation as the foundation, that's the approach that we took when we wrote the Delaware site evaluation guidance. And this is a Delaware-specific document that was published just this spring with the goal of providing resources for practitioners to walk through a systematic and repeatable site evaluation where we're collecting data and information and hopefully digesting that in such a way that starts to inform a concept design and inform which techniques you might use, which is the subject of, I think, the next talk with Chris. So the guidance includes, we'll just round up to about 50 pages of content, including a worksheet. Now this worksheet, which I'm showing now, includes both desktop analysis parameters and site visit parameters. We recommend looking at the desktop analysis first for a couple of reasons I'll go into later, but it's going to help provide that perspective on how much data is available and what you might need to collect subsequently in the field. It's also important to take a lot of photographs, and I think I have some slides. I'm getting ahead of myself. Photographing your site is critical to painting the full picture, and I do have a slide later on where I'll talk about that. So let's dive into the pre-site visit desktop analysis portion of this guidance. We're going to want to collect information generally on the site description, your shoreline orientation, any information you can find on the geomorphology and change rate of the shoreline. And then, as I mentioned before, waves being the primary erosive force of a shoreline, we're going to try to quantify the waves present at the site, and as well as understanding things about the tide, the normal tides, and the storm tides. And the tide levels, or the water levels related to tides, are important for your choice of marsh grass and vegetation habitat, which I think you learned about last week a little bit. So the very first, and I think the most important thing to do when you take on a new client for a living shoreline project is to understand what the problem is and what the property owner's goals are. Now, I mentioned before the Delaware SAA, and in order to fit under the umbrella of the SAA and use that streamlined permitting avenue, the project needs to be addressing an erosion problem. You might have a client who just wants to pretty up their shoreline and doesn't really have an erosion problem. That's fine. You can still install a living shoreline, but you'll need to get an individual permit from the Wetlands and Subaqueous Land section, which Julie will talk about tomorrow. There might also be secondary goals that a property owner has. Maybe they do have an erosion problem, but they really want to make a visually attractive shoreline. They don't want to see any rocks. So understanding those goals from the top will help you steer your observations of the site and develop your concept design. Some administrative stuff is important to capture, especially if you're working on a team. And because not all of you are going to be doing this desktop analysis at the same time, and especially not your entire team will probably have the opportunity to go into the field together. So including information about the location of the property, it seems obvious, but the location of the property, the owner, document the problems and the goals and make sure that the owner understands and acknowledges that that is exactly what they meant. So we're using this example in Lewis, Delaware, that is adjacent to the Little League baseball fields. There is a living shoreline installed near this site, and adjacent to that installation, I should say that that installation has been successful for a number of years. You may be familiar with it already. A couple other speakers may have talked about it. But adjacent to that successful project site, there has been ongoing shoreline erosion, and that is indicated in the circled, in the orange circle on the figure on this site, this screen. The goal of this property owner, using this as an example, is to repair damage and prevent future erosion, and some site dimensions that are rough measurements using an online mapping platform such as Google Earth, or if you're sophisticated and savvy, you can use ArcGIS or some other map-based platform. This is not the time necessarily to go out and send a survey crew and get precise centimeter level site dimensions, but we're calling this a site about 115 linear feet along the shoreline. Identifying the water body can be important in terms of identifying whether a site is saline or tidal. So just important to document that. The orientation of the shoreline, we like to recommend using a 16-point compass. Again, not the time to go out and send the survey crew necessarily. Being approximate is usually good enough. So if I draw one line along this 115-foot section of shoreline, I can say that the general orientation is north-northeast. Okay, and this is going to come into play when we're looking at a couple other parameters like wind, which we know drives waves. If we have an exposure to a predominant wind vector, then we know that wave energy may be enhanced at this shoreline. The shoreline change rate is important to understand historical context for any erosion that may be present. The Delaware First Map GIS server has a great repository of historical aerial imagery from 1926 to 2017, and I believe they have a plan to collect new imagery every few years, so check back. But that can give you a good indicator on whether or not the shoreline location is changing, whether or not there's been erosion or accretion. One tip that I'll share is that because of those old images are manually georectified in the system, their location in space is not precise. So if you are looking at an old image and you were to draw a line on your computer screen and then turn on a new image, you might notice a change in the shoreline location that's not due to erosion, but rather just due to the location of the image that you're looking at on the screen. So try to find a road or some other permanent feature to measure from when you're looking at shoreline location, because that is going to be relatively consistent from image to image. If you're lucky enough, there are products out there and available that already quantify the erosive condition of a shoreline. VIMS, the Virginia Institute of Marine Studies, has an inventory of shoreline conditions throughout the Chesapeake, and we're lucky enough in Delaware to have some information in the Indian River and maybe one other water body that I can't recall right now. But check for existing resources during your desktop analysis to make your life easier, and because that is a credible, proven source that's repeatable. The geomorphology that we look at in the site evaluation is broken up into 3 different sections: submerged, along the shore or bank, and in the upland. And it's important to try to identify as many features as you can using the resources available to you. But I know a lot of times it's going to be hard to identify these big geomorphologic features in aerial imagery because the water in Delaware tends not to be the clearest. In this example, though, near Cape Henlopen, you can see that during low tide, we're getting a lot of sandbars exposed on the western side of the Cape, which tells me that there's a lot of sand and a shallow sloping near shore in the submerged zone. For upland geomorphology, you might want to look at existing LIDAR or survey data sets that tells you what the contours look like, and things like the NOAA navigation charts might tell you a little bit about what the offshore is doing if you can't see it in the imagery. The next few parameters are all focused on quantifying your wave energy. So I'm sorry I didn't attend last week's talk where Joe talked about waves, but suffice it to say it's a complicated subject. Basically, we can generalize into a couple statements, right? Water waves carry energy to the shoreline. They are generated by wind acting over the water over a certain distance, and that's fetch. And they are controlled by things including the depth of the water column. So knowing those couple of things, we're going to look at the fetch first. We recommend using that shoreline orientation and looking at the 5 nearest fetch directions and measuring them. And I'll note on this figure, on the example from the Little League ball fields in Lewis, the north-northwest fetch direction, the measurement includes the low-lying marsh area to the north of the canal. So pay attention, don't automatically stop your measurement at a visible shoreline. If you know that it's low-lying marsh that might be inundated at high tide, waves can be propagated over that distance, and so it might actually lead to a longer fetch measurement for you. Winds are some of the most complicated and difficult data to obtain, and we have some resources listed in the site evaluation guidance, as well as some rules of thumb for Delaware. We did some data processing and gave you some kind of default numbers that you can use if you're in the right vicinity, southern Delaware. But in general, resources I want to point out are the Delaware Environmental Observing System, DEOS, which has a good spread of gauges across the state and will allow you to request large, long history data sets. And also, we can recommend taking a look around for some specialty websites. There might be a website dedicated to sailing or fishing or something that includes information that's relevant to your project. We like this one for windsurfing because it does some of that data processing for winds. One thing that we need to stress is be careful when you're downloading wind data or any type of environmental climatological data, because the units might be different from what you're used to working with. The direction convention might be different from what you're used to working with. For example, you might be used to reporting wind from, and something else might be used to reporting a wind to. And then wind especially, your weather sites are going to usually report a wind speed at 10 meters off the ground, so you're going to need to convert it to a surface level wind for fetch calculations. We have some resources in the guidance that help you do that as well. Waves are what we're trying to arrive at. We want to know what our typical wave might be at a site because that tells us our energy regime. There is a great USGS created a tool online, we linked it here and in the guidance, that helps you determine your wave height and period based on wind speed, fetch distance, and water depth, the three parameters that I mentioned early on that we know generally contribute to a wave size arriving into shoreline. I recommend playing with this a little bit to get familiar with it, but we found this to be a really great tool. Tides are tricky because tide gauges are sparse, especially in Delaware. So get creative with how you try to find this information, even though a true NOAA tide gauge only exists at in a couple locations, for example, in Lewis. We know that the University of Delaware periodically puts out water level gauges. DelDOT has water level gauges. There might be other networks that you can tap into for this kind of information that just may require a little bit more processing. But you're after the mean high water, mean sea level, and mean low water. Those are some benchmarks that you're going to use to help design your low and high marsh platforms in the future. Also, capitalizing on existing work, right? Storm surge and extreme water levels are very hard to compute, but luckily FEMA does that for us. So Delaware has a flood planning tool that lets you navigate to any site, click on your site, and it tells you your flood zone. So using the Little League ball field in Lewis as an example again, we know that this is in an effective flood zone AE, which means it's coastal, there is some wave energy, and the base flood elevation is 7 feet. I'm running out of time, so I'm going to have to speed up a little bit. But the site visit parameters, you can see here. Some things you just cannot tell from aerial imagery, or necessarily you need to be on the ground to observe certain things. And that's where we want to stress a site visit. You can capture things that you could not tell before, and you can verify or validate some of the stuff that you observed in your desktop analysis. I promised a slide on photographs, and here it is. We recommend taking as many photographs as you can. You will probably not regret taking too many. You will definitely regret taking too few photographs. As I mentioned, your entire project team probably won't have an opportunity to go out into the field with you. So taking photographs is a great way to communicate the lay of the land to other team members that you may bring on later. Include scale objects in your photos. This is important. It could be a person, it could be a clipboard, it could be a pen. When you're taking a picture of something that is mostly marsh grass or sand or water, it is very hard to tell a scale. So put something into your photograph that will help you in the future. Take careful notes, and pay close attention to your site boundaries. Any kind of intervention techniques or things that you install are going to need to tie in to the neighboring property at some point, or tie into high ground or something at some point. You can see from this picture that there's a rock revetment that just kind of stops, and the neighboring property has a sandy beach, and water can easily wrap around the end of that rock revetment, rendering it less than useful in this case. Your land use and land cover, both in the upland and water areas, are important to note because they present the constraints that you'll have to work around in your design. You will be able to tell things about the geology from the site visit that you couldn't tell from desktop analysis, most likely. Again, this is broken into 3 sections: submerged, along the shore and bank, and in the upland. Definitely observe things that you couldn't ever tell from the air, like high water marks, sediment characteristics. You can, at this point, again, not the time necessarily to take a sample and send it off to the soils lab, but if it's sandy, observe that. If it's sandy and silty, observe that. Taking notes that will help us decide what to do in the future. The local ecology. So you heard last week a couple talks about ecology, both flora and fauna. Observing the ecology that's on site or near to the site is going to be one of the best things you can do to decide what might be successful on your site. Also note any abiotic variables and you might be able to tell this is where I get a little uncomfortable in this talk. I do not have this ecological background, but note your abiotic variables that are going to play a factor in the success or failure of different ecological techniques that you're trying to implement. For example, the water salinity, sunlight and shade factor. We know that most marsh grasses need full sun to thrive. So if you have a large tree canopy, that will be important to note so that you can choose your vegetation plantings accordingly. To complement your photographs, you're going to want to sketch the site, and we have some examples in the guidance document. But we recommend doing a profile as well as a plan view. A plan is from the top down, a bird's eye view that helps you establish the relative position of different things like the shoreline, any structures that might be present on site, a driveway, things like that. And your profile will help you establish the presence of maybe different marsh grasses at different elevations along your profile line. On the site evaluation worksheet, I showed you before the 2 pages of data collection parameters. We also gave you 2 pages of a grid to draw your site sketches on. And again, we have some examples here that you can use as inspiration. Lastly, I want you to make sure that you're validating the observations from the desktop analysis. And I'll use my own personal experience. In Dewey Beach, there was a site that we were looking at where a long fetch distance extended to the south-southeast from near the top of this picture on the left-hand side. Once we got out into the field, we noticed that the orange circled pier, what looks like a pier in the aerial imagery, is actually a breakwater. It is solid down to the waterline. So waves cannot propagate past that, which means that fetch measurement that I did initially on the desktop analysis was invalid, and I had to go back and redo it, which changed the expected energy regime for the site. Also, it's a good chance to observe things like boat wake, boat traffic near your site, which may be kind of that wild card factor you need to consider for energy arriving to your site in the form of waves that are not wind generated. And lastly, the past 2 or 3 years, we've held a full-day workshop on site evaluation that includes a major field component. So it's half-day classroom, half-day field, where we're looking at 3 demonstration sites and walking through the site evaluation guidance and worksheet along with the students. This has been very successful in the past, and we look forward to continuing it in the future. It was originally scheduled for April. It has been postponed, but keep your eye out on the website that's linked here for updates. And I'm not sure if we have any updates from Brittany or Kenny on the Outlook right now. But if we can hold it in person in the fall, we're going to look to do so. If not, we may try to do a virtual type site evaluation workshop. So if you're interested, let us know. I'm not sure we have time for questions, but here's my contact info. I'd be happy to answer anything via email.
Now we are going to switch over to Chris to talk about materials and their uses. And Chris, I will let you introduce yourself. You can take it away.
Great. Thanks, Britt. You guys can hear me and see my screen okay?
Yep, you are good.
Awesome. So my name's Chris Pfeiffer. I'm a senior consultant with a firm named Cardno. Before all this started, I'd sit in Newark, Delaware. Now I'm at home like everybody else. I've been involved in coastal restoration, monitoring, and assessment in some shape or form for the last 25 plus years, mostly in the context of restoring oil spill impacted habitats, but more recently in some non-regulatory work, including living shorelines for shoreline stabilization, ecological uplift, et cetera, et cetera. I'm a member of the Living Shorelines Committee, and I serve on the Engineering, Design, and Regulatory subcommittees. So what we're going to try and do here the next 45 minutes or so is kind of take a next step and expand on some of the concepts and assessment techniques that Jesse just described and that you heard about from our speakers last week. We're just going to quickly review some key concepts We're going to talk about, it's kind of a blend of materials, living shoreline construction materials, and design. It's a little difficult to separate the two, as you'll see as we go through the next couple slides. And then I'm going to wrap up with a case study to try and demonstrate some of these principles in practice. So just before we get started, so we kind of establish a little bit of a common vocabulary, here's a couple of the terms that you'll probably hear me talk about as we go through this, and things to keep in mind as you're starting on thinking about. I like that graphic that Jesse had in the last presentation, that progression from concept design through refinement, coming up ultimately with a final design. So we think about this in terms of structural elements or the pieces or parts of a structure, and you'll see that as we go through some of these examples, but it's kind of the building blocks of these designs. And when I use the term materials, I'm really referring to what are those things made of? What are they? Some of them are natural materials, some of them are man-made materials, as we'll see, and they're typically used in combination with one another to accomplish a particular goal. So sometimes we'll use the term strategy or technique to refer to typical but yet still conceptual arrangements of how we put these basic building blocks together to accomplish specific objectives. And then finally, and I think of this as the most refined and typically the last step in this design process, is the actual design. And that's where we're taking these building blocks and these various materials and we're arranging them, but we're defining the specific dimensions and quantities and the exact arrangement of how we're going to use these materials to construct a project. And I think of that kind of as the final design or the specification. That's what we're going to look at in the field. That's what you're going to send out to contractors to say, okay, this is what I want to build. I want your insights. I want your cost. And that's kind of the blueprint for moving forward with taking a project from the very initial idea phase all the way to putting it on the ground. So I said this a second ago, and I think it's somewhat hard to put down the specific order in which this process goes, but what I try to do is capture in broad brush kind of how I tend to think about it, and I think other folks in the industry think about this. Jesse mentioned it. Really, it starts out with your goals and objectives. So what am I trying to accomplish? Typically, that begins with a problem. You identify the problem, and then the goal is to solve that problem. And the example that he used, and a big driver for a lot of living shorelines, is shoreline erosion. And then, as Jesse talked about, understanding our site conditions, that's key to, we need to understand what we want to do. If we want to fix something, why is it broken or in need of fixing? So our site conditions help us understand that. And then that really feeds into our project design, whether it's conceptual or you go along that progression in more and more refinement to a detailed design. But that's okay, we know what we want to do, we know what the problem is, or we think we do, but how are we going to fix it? So it's starting to get our design is really our solution, and that really drives the selection of materials because not all materials are suitable in all locations. So I kind of think of it this way. It's sort of this Venn diagram, this overlap of, you've got your project goals. Up here, what is it that I'm trying to do? What kind of conditions am I dealing with? What's the nature of my site? Because that's going to, A, tell me about the problem, but also the forces, the energy environment that my design and my materials need to withstand. And we'll talk about this in a little bit more detail coming up, what are the attributes of the various materials that I have to choose from in building a living shoreline? And really, it's this overlap of the three that's going to help you select your materials and influence your design. So I won't spend a ton of time on this because other speakers have talked about it, but there's kind of in three broad categories, kind of the goals of living shorelines. So most commonly, it's to stabilize an eroding shoreline, and I think of that as I just don't want it to get any worse. I know there's a problem. I'm not going to do sort of what we have in the second bullet here, which is restore the eroding shoreline. So that's kind of stopping the erosion, but then actually taking it back to some prior historic condition and reclaiming lost shoreline. So that's kind of the second, that next step beyond I just want to fix it. So in that one, I want to fix it, but I also want to make it better back to some maybe historic condition. And then a third and quite common objective more recently is there are these ecological uplift objectives that I want to achieve. So whether that's habitat restoration or creating new habitat or enhancing degraded habitat. And one of the key differentiators here is on your list of project goals and objectives would be this idea of creating some kind of ecological services or uplift. Not that the project doesn't provide shoreline stabilization as well, it's just that the vision is a little bit broader than just stopping shoreline retreat or taking it back to some previous condition. And many projects accomplish all of these things or some of these things. So you don't have to pick just one. It's okay, and projects that achieve multiple benefits, you're getting more bang for your buck than projects that are more narrowly focused on solving just one specific problem. So as we talk a little bit more about designs, some of the things to keep in mind is where is a living shoreline? Where is your design going to be applying materials, constructing structures relative to the position of either the current shoreline or some historic shoreline? And you can broadly categorize living shoreline projects relative to this. So there's kind of a progression. So you've got, in the upper left, you've got these projects that are right at the edge of an existing shoreline. This looks like it's oyster shell bags put right at the edge of an eroding marsh, kind of a marsh toe revetment using shell material. Similar design, but it's moving offshore, either moving offshore a little bit or the shorelines continue to erode. And then you can just see this progression. These are, what I'm going to guess, are reef balls or oyster castles just offshore. So they're providing an energy attenuation function. A toe sill, and we'll talk in a little bit more detail about some of these techniques. And then you've got these other classes of projects. These are wave attenuation devices or WADs or maybe reef balls, and they're significantly offshore. And they are designed to work by a slightly different mechanism by just reducing the wave energy that's impacting the shoreline. So with that kind of general orientation, let's jump in a little bit about the actual materials, the building blocks themselves. So we're going to cover, what is this, nine or so different types of materials, ranging from, the purely natural to the highly engineered. And there's no, people have their personal feelings about whether or not they, how much engineered material they want to use. And what I would say is keep an open mind. There's a time and place for all those materials potentially. But if you want to limit your use to more natural materials, there's certainly nothing wrong with that either if those are appropriate for your site. And as we go through this, hopefully we'll learn a little bit more about how to determine what's appropriate for particular sites. So one of the ways that I find helpful to think about understanding materials and then using that understanding to help in the selection process is to think about what their job is, what is their function, and how will each individual material or material type contribute to achieving the goals and objectives of my project. And what I try to do here, this isn't necessarily a comprehensive list of all the things that these materials do, but in general, you can kind of think about materials as doing one or more of these key functions. So they're either going to raise the elevation of the bottom, and we'll talk about why that's important. They're going to provide some protection to the front, the channelward edge of our project, either the existing bank or the toe of a new slope. They're going to help stabilize or retain fill material that may be placed along the shoreline. Energy attenuation is a key function of a lot of these different materials, whether that happens right at the shoreline or if it happens a little bit further offshore, like some of those pictures I showed a few slides ago. And then for those types of projects which are focused more on ecological uplift, a along with some wave attenuation benefits, are the materials really more of a substrate or a scaffolding for reef building organisms? So they've, you've got a biological component ultimately, but it starts out with some hard substrate for colonization. And then also, in addition to those functions, we think about a bunch of different considerations in how we would evaluate or think about the materials. So what's it made of, its composition? How will it be used in our design? That's what we just talked about on the last slide. What purpose does it serve? How is it going to contribute to my goals and objectives? I also need to think about its availability. It's great to have the perfect material, but if you can't get it or you have to ship it across country and your logistics costs go through the roof, then that doesn't really do you much good. It's constructability, and by that I mean sort of, is this something that a group of volunteers can do? Can you, is this basically manual labor, or do you need specialized skills or heavy equipment? Not that that's not available, but it has impacts to the cost. A big consideration, and we'll spend a little bit more time talking about this as we work through these materials, is the durability or the longevity of these materials. So is it able to withstand the energy at my site, and how long will it last? Some of these natural materials are biodegradable, so they serve more of a short-term function. They're a temporary component of your design versus a permanent component, and that can have important implications at different sites depending on what you're trying to accomplish and what your site conditions are. Aesthetic considerations are very important and more important to some clients in some applications than others. Is it natural looking? Is it nature-based? Depending on where you're building your site, that may be a requirement. You're working along a shoreline at an industrial facility, they may be less interested in aesthetics and more interested in function. And then really just kind of catch all of other considerations. Are there other nuances specific to the materials that you're working with that can and should be part of your consideration in thinking about, is this the right material to use as part of a design at my site? So this is kind of the list of criteria that we're going to work through generally as we talk about these various different materials. So I'm going to start with sand fill, mostly because it's one of the most common structural components that's used in living shorelines. Unless you're just, putting some physical barrier at the front edge of an eroding shoreline, most living shoreline designs, I won't say most, many, include a backfill component, and sand is the common material for that. So typically what we're looking at is washed sand that's imported to the site coming from a sand pit. From somewhere nearby. In Delaware, that's an easy proposition because it's one big sandbar. There are instances where sand from offshore is dredged and used back up on the shoreline, more complex in terms of the engineering, the permitting, and more costly. But regardless of where you get your sand from, its primary function is to raise the elevation of the bottom, and we'll talk about why that's important in a little bit, and also as a planting substrate. If you're working here in Delaware, the Mid-Atlantic, Virginia, Maryland, Chesapeake area, New Jersey, sand is plentiful. There's an abundance of it in this part of the world, fortunately. And it's not terribly expensive. The cost is really driven more by how far you need to bring it in, so trucking, shipping costs. Unless you're willing to invest a lot of sweat equity in a project and you don't have very large quantities, it does usually require at least a bobcat or some kind of small equipment or excavator, bulldozer to move around. It is pretty easy to work with, that's the good news. In terms of its durability and longevity, it's very persistent if the wave energy is such that it will stay in place. And that's usually dictated by other components of your design, sometimes just your site conditions. But your site conditions in combination with other components of your living shoreline will help create this energy environment that will allow the sand to persist. Aesthetically, people like it. It looks kind of like a beach. It doesn't catch your eye as out of place on a shoreline. And then just in terms of other things to think about, it's important to have compatible grain size. If not, you can have sand that's too fine a grain in an otherwise coarse environment is more prone to being washed away and transported off your site. Therefore, it's not really going to serve its function in the long term as much as you want. And depending on your situation, it's recommended to allow at least a couple tide cycles to go by so that your sand settles in place. One of the things that's nice about it is it's not really prone to soil compaction in the same way as some of the other more organic substrates are. So just the fact of, backing over it with a bulldozer a couple times beds it down pretty well, but it's always recommended to let at least a couple tide cycles go through so that it kind of seeks its own level because that elevation, as we'll see, is pretty important. All right, so in terms of the next, I would say, most common building material for living shorelines is Coir Logs. So when we say Coir, you're probably familiar with that term, but it's the fibers from coconuts or the coconut husks. And it comes in a couple different formulations. When we talk about logs, it's typically this loose fiber that are encased in these mesh tubes. They kind of look like these giant sausages. They're anywhere from about a foot to maybe 20 inches or so in diameter, 10 to 20 feet long. And they're really designed to establish, as you see in this picture on the lower right, establish the toe or the front leading edge, channelward edge of a living shoreline, and then they help retain fill. So typically sand would be backfilled behind here, and this is going to help that sand from just washing out every time a wave laps up on here and retreats back offshore. It's also a planting medium, and it's biodegradable. That's, I think, one of the biggest reasons that it's used is because it's in those instances where folks are hesitant to use more durable material for aesthetic reasons or whatever, biologs are perceived as being a greener solution because they're biodegradable. They're made out of natural material. They're readily available. I think last time I looked for them, there's definitely specialty suppliers that provide them, but I think you can even get them from Lowe's now as a specialty order item. I don't think they're on the shelves, but shouldn't be any trouble getting these if you want to use them as part of your design. They're very easy to work with. They're bulky. As long as you keep them dry, they're fairly maneuverable. You can bend them around to configure them to various shapes along a shoreline. They're very amenable to manual installation. You have to drive these wooden posts down a couple feet, and honestly, that's probably the most difficult portion of it, depending on what kind of substrate you're in. Unless you get them wet and then you realize, oop, I need to rearrange them a little bit, then that can be a little problematic because they get very heavy very quick. I think one of the biggest considerations and potential downsides for their use in certain situations is their longevity. They are a natural material, and I've seen them last maybe up to 7 years, but they're looking pretty ratty. I think 5 years, maybe 3 years on the short end. 5 years is probably a pretty good rule of thumb about how long they'll last. And if you subject them, even when they're new, if you subject them to high energy, high wave energy environments, they're not as durable as some other materials. So I think one of the key considerations for biologs, they have their place, but it's very important to think about what's going to happen to my shoreline, what's going to happen to the functionality of my design in 3 to 5 years when these Coir Logs have biodegraded. Will I have lost an integral component of my design, or are they really only intended to help stabilize the site in those critical first few years while other components, primarily vegetation, are getting established, and by the time the biolog has degraded, the vegetation will be mature enough that it can stabilize the shoreline. So a slight variation on the Coir Log is the Coir Blanket, and it's the same material. It's just woven into these, large weave mats, and it's used in a couple different applications. A lot of times this is used in upland soil and erosion control just to hold slopes in place once they've been seeded until the plants germinate. But here they're used on shorelines in a couple different ways. Most commonly is just to hold the shoreline in place, and then you can plant through them. That's what you see in this lower left-hand corner. Up here is an application where we actually grew plants in Coir Blankets. We actually had a nursery grow them, and they grew them up so that we basically had what I refer to as a sort of salt marsh astroturf. They roll them up, so I think they were 20 feet long, and they grew them up to a foot high or something like that, rolled them up, shipped them to the site, and we were able to unroll them and stake them in place and have the benefit of more mature vegetation and the energy attenuation that it provides sooner rather than planting sprigs and waiting a couple months until the plants were as mature. So the one last caveat I'll put down here is when you're selecting your core material and mattresses or blankets, it's very important. There's a lot of products out there that have a plastic mesh backing built into them, and typically they are not preferred in living shoreline applications because of, once all the core material breaks down, you're still left with the plastic. So, we don't want to have wildlife entrapment or entanglement issues. Rock in certain applications is also a very common living shoreline material, particularly in revetments or what are called toe slopes. We'll talk about that in our case example. It comes from stone quarries. Very little rock at least in southern Delaware and other parts of the mid-Atlantic. So it's being shipped in from Pennsylvania or Maryland. So there's some transportation costs. It serves a similar function to a biolog. It's just a little bit, it's significantly more durable. Because it doesn't biodegrade through time. If it's sized correctly, it's a permanent feature of a living shoreline, and it's able to withstand fairly significant wave energy. It serves a similar function. It holds fill in place, and it attenuates that. It's that first strike when a wave impacts a shoreline. It can help absorb that energy, or at the very least help cause that wave to break a little bit further offshore than it would if it were naturally moving up the shoreline. It does require, it kind of ups the ante in terms of the amount of equipment that's involved. So you got to get it out to the beach, and then once it's out there, you've got to arrange it. So depending on the size rock you're using, that can be done with like a mini excavator with a claw or a thumb. But if you're working with larger rock and higher energy environments, it does increase the size of the equipment that's needed. It is appropriate for use at moderate to high energy sites. There are limits to that, as Jesse talked about in his Lake Erie example. But as we'll see, it's appropriate in sort of those energy regimes that are within the capability of a living shoreline to stabilize and restore shorelines. But in those conditions where you wouldn't necessarily want to use a biolog due to either the initial energy or the longevity, the fact that a biolog is going to go away after a certain period of time. There are some concerns, depending on who you talk to, about the aesthetics of using rock in living shoreline. It does have a more engineered look to it. It's definitely a structure. You look at it and say, yeah, that's a man-made structure versus other design techniques with a biolog. You may have a hard time distinguishing that it is a restored shoreline. And then just from a design perspective, it does require, it starts to bring in the need for some civil and coastal engineering type expertise to make sure you're sizing it correctly. Plant material, this is, aside from the sand, which is abiotic, this is kind of what gives most living shorelines the living part of their definition. So, and Bart talked about plants quite a bit last week, so it's appropriate that they be appropriate to the salinity regime, to the habitat that you're working in. They really help stabilize sediment, they attenuate wave energy, and they provide the ecosystem functions, all those good things that marshes do. One of the things that I think is key about plants in building living shorelines is that they're one of the components that leads to resilience and self-repair. So even after a storm, a site may get beat up a little bit, but as long as it doesn't get completely wiped out, the plants have the ability to heal. They'll fill in, they'll restore themselves to a large degree. They're pretty available. sometimes projects salvage plants from the wild. There's some regulatory concerns with that. There's some cost effectiveness concerns. So most projects will purchase plants from a native plant nursery, and fortunately there's growing numbers of those around. It's very amenable to volunteers. It's manual installation. Rarely will you have, even on large sites, the need or the ability to use machinery to install plants. In terms of their durability, they need to be paired with the right kind of tow protection depending on the energy of the site. They're appropriate for low to moderate sites with the right kind of tow protection. Real high energy sites, if you don't have vegetation growing there already, there's probably a reason why, and it's most likely related to the energy environment of the site. I think Bart talked about in his talk last week, herbivory protection. That's one of the biggest concerns. Whether you're using bare roots, plugs, or pots, that's more of a cost concern. And you really need to think about and understand the elevations and the hydrology. Bagged oyster shell is gotten more and more common. It's used both for physical protection at the toe of slopes and also as a biogenic reef building substrate. It can also be used in offshore settings for wave attenuation and causing waves to break before they hit the shoreline. Again, it's within the capability of volunteers to use this. It's largely done with manual installation. You may be floating, several bags offshore in a dinghy or something like that, but they're hand placed. You don't need machinery to do this unless you're putting out large quantities of uncontained shell, but that's not really what we're talking about here for living shoreline settings. You need to be careful about the energy environment that you're using. These are most appropriate for low, maybe some moderate energy sites. And if you're in a location where you expect them to get colonized by oysters or rib mussels, they can be self-sustaining. However, I think one of the important considerations is what happens if you're working in a setting where you don't expect rapid or any colonization. What happens to these once that plastic breaks down? So in some respects, I think of these along the lines of a biolog. If I don't expect them to be colonized and encrusted with mussels or oysters, eventually they're going to break down. So I'm going to lose my structural stability that these provide, whatever function that would have been. And there's a growing concern about microplastics and debris in the marine environment and how they might contribute to that. Oyster Castles are another one of these engineered substrates designed to promote reef building. They're pretty available. I think there's, this is focusing on Oyster Castles. I think there's one or two competitors out there now. There are these modular units that are used to build reefs. I think Josh will probably be talking about in the monitoring section one of the projects that they did in Delaware that use these quite a bit. So they have their time and place. Working within the intertidal zone, we don't see a lot of persistent oyster reefs. So this is something that may be more in the subtidal zone. So it may be out in front of a living shoreline that's constructed with other techniques. So it's a component of it that's intended for both reef building as well as maybe some energy dissipation, causing a wave to break a little bit sooner, so that when it does encounter your living shoreline, it already has a little bit of that energy knocked off. Reef balls are kind of the same concept, but just scaling things up. They're a hard substrate. They're designed to be a scaffolding for biogenic reef building. The term reef ball is a proprietary term. Last time I looked, I'm not sure the Reef Ball Foundation. I think they're in existence, but they're not as prevalent as they used to be. A lot of volunteer groups are doing work with these. They purchase the forms and they pour them themselves. So the smaller ones, two people can lift. Once you start getting to the larger stuff, you do need some, equipment to put them out, either a boat with a winch and an arm, or a barge with some heavy equipment. Although they create oyster reefs, they can have more of an engineered look, and they're typically deployed a little bit further offshore or maybe just offshore of like a leading edge of a marsh. And then sort of the grand poobah in that same category would be the wave attenuation devices, or WADs, although these are really intended to absorb and dissipate, break up wave energy. So in certain settings, they may become encrusted and be a substrate for shellfish colonization, but they're intended to work just by sort of breaking up the wave energy and shooting it off in multiple different directions. They're not for every site. They are expensive. They're difficult to work with. They've got some aesthetic concerns. So we've used these at a refinery on the Delaware River, like I said, where aesthetics are a little bit less important, or they're used a lot down in Louisiana where aesthetics are still important, but they're losing so much marsh that the functionality overcomes the aesthetics concern. And because they are put offshore, they can be much more of a navigation hazard. Timber logs, not real commonly used, but they can be. Not in this part of the world, we don't see a lot of large driftwood, woody debris used on shorelines, but again, logs can be used to hold tows and slopes, to dissipate wave energy, attenuate wave energy slightly offshore. So there's been a couple projects, but I included them here because they are sometimes used. I would not say that they're a real common living shoreline material. So with that, we're going to jump into a case study. Britt, I got about 15 minutes left, so is it all right if we jump over the allotted time a little bit?
Yep, no problem. We have a break in there. We can use the time in that to go for it.
Sounds good. All right, so I'm going to shift gears right now, and we're going to talk about a living shoreline project that was constructed a little over a year ago down in southern Delaware at a place called Sassafras Landing inside of Asselman Wildlife Area, which is owned and managed by the Delaware Division of Fish and Wildlife. So this project was a partnership between the Delaware Center for the Inland Bays and DNREC Fish and Wildlife. And we were involved in kind of taking the conceptual design into final design and assisting with construction oversight. A lot of folks on this panel and within various organizations of DNREC contributed to this project in a variety of different ways. So it was a really nice partnership. And I think a good example of both the design process and some of the construction techniques. So you can see down here, it's located in Little Asselman Bay, which is one of these coastal estuaries. It's just south of, it's one of the Delaware's 3 inland bays, the kind of the lesser known inland bay. So we'll look at a ground level photo of this circled area right now, but I think the big takeaway here is that we've got a tidal estuary out here, Miller Creek, and it's kind of difficult to see in here because a lot of vegetation, but this brown area down here is a freshwater impoundment. So there's debate about the appropriateness of freshwater impoundments, but they do provide a lot of habitat diversity. And in this particular case, the management objective was to maintain and preserve this freshwater impoundment. And the situation was that this impoundment was created sometime back in the 50s and 60s by essentially creating an earthen berm and sectioning off some tidal salt marsh, and over time it transitioned to a freshwater impoundment. As a result of sea level rise, shoreline retreat, storms, this berm was in jeopardy. And at its narrowest point, it was about 10 feet. What you can't really see in here is there was some haphazardly piled riprap that was sort of an emergency fix after one of the coastal storms several years ago, as the wave energy from Miller Creek continued to sort of eat at this berm. So the concern was, and this is the problem identification part of the design, was that the ongoing shoreline retreat, wave erosion, wind-driven waves, and boat-driven waves would continue to erode this shoreline until it eventually breached this earthen berm, and there was basically tidal connection between Miller Creek and 35-acre pond. So just a little bit about the shoreline conditions, the existing conditions. There was essentially no low marsh left. There was a very narrow fringe of high marsh, most of which had been overtaken by Phragmites, a lot of undercut banks, root wads and tree stumps out in the water. Here's a shot of that, that riprap that I mentioned a second ago. Here's another picture. This is always a good indication of shoreline retreat when you've got hardwood tree trunks out offshore. You know, at one point that was upland. So with DENREC's help, we did a little bit of aerial photo reconnaissance and learned that, you know, we had about a ½ foot a year of shoreline loss, which doesn't sound a lot in any given year, but that adds up over time. So given that we had a narrow spot in here of about 10 feet, it was only a matter of time. And again, shoreline erosion tends to be episodic. You know, we express it in terms of averages, but it's really not. It's no erosion under a lot of conditions, and then you have that nor'easter or that coastal storm, and you lose a couple feet. So don't misinterpret ½ a foot a year as, oh, this has 20 years before it was going to breach. So we worked with the various stakeholders and the landowner and came up with a list of project goals and objectives that really focused on restoring the lost shoreline, enhancing the wetland and aquatic habitat, and increasing resiliency of this particular shoreline. And it turned out that this was done through stabilizing just a little bit less than 400 linear feet. And in the process, we created about a ¼ acre of fringing salt marsh. Some of that was reclaiming and restoring marsh that had been completely lost. The overriding objective was to prevent this imminent breach and the continued erosion of this earthen berm separating the creek and the freshwater impoundment. And along the way, we reduced the nutrient loading by keeping soil on the bank rather than in the estuary. Allow this shoreline to respond and react to sea level rise better than it was in its current form. And last but not least is this was also done as a living shoreline demonstration project that's open to the public to go look at and see and understand. There's a good monitoring program for this. So we started off, as I mentioned before, we got the conceptual design, and we really kind of looked at, well, what do we know? And then what do we need to figure out? So we knew that we couldn't grade the slope back because we didn't have enough width. Remember, we had about 10 feet of berm intact remaining width. So we really knew that we wanted to build a bigger shoreline, and we knew we had to build out into the channel. So what that told us is we're raising the bottom elevation. And then that really led to a couple questions, and this helped inform our design process. So what are the species that we're trying to grow there? What's going to be the plant material for our living shoreline? And we knew that based on the surrounding environment. In this case, it was salt marsh. How high do we need to fill? What elevations do we need to achieve the hydrology that will support the species that we want to plant in there? And then most importantly, I think, for this design was what kind of tow protection did we want, if any? So our choices really were nothing, Coir Logs, bag shells, the reef substrate, or quarry stone. So similar to what Jesse showed, we went through a very similar site evaluation process. We looked at fetch as the primary determinant of wave energy, which was sort of the primary determinant of what we wanted to do in terms of tow protection. So here we had a maximum fetch of a little over a ½ mile, but again, this extends further because, as Jesse mentioned, you don't necessarily want to just stop it at a marsh edge because sometimes this is going to be flooded. So on average, we had about 0.2 of a mile fetch. So if you look at most guidance, this would suggest, you probably don't need to go to like a tow sill. So we started thinking through what the options here. So we didn't choose Coir Logs because when we look at the existing conditions, it was clearly an eroding shoreline. So the thought process was once that shoreline has eroded, once those biologs have degraded, we're going to be right back in the same situation that we are in now. So while the Coir Logs would provide protection in the short term, eventually they would degrade, and we were concerned that there needed to be some long-term protection so that we didn't just repeat the cycle that we were in. We thought about reef balls. But they don't retain fill, and we're not necessarily in an area where we expected colonization by oysters. So that kind of took the bag shell out of the running as well. So they would have worked in the short term, I think, with the energy regime, but eventually once those plastic mesh bags broke down, we'd have just loose scattered shells, so that may not provide the same structural functions of retaining fill and attenuating wave energy in the long term. So we didn't select that. So in the end, we decided that the best combination of durability and longevity would be rock in a toe sill arrangement. There was already a good example of that actually right next to our project site. You can see, if you can see in this picture, this is the project site, and just on the other side of this little unpaved boat ramp, there was a toe sill-like shoreline structure already in place. So real quick, because I know we're getting to the fun stuff but running out of time, this was kind of this toe sill, this was a general concept design, and really to take a concept design and make it a site-specific design, we needed to know a couple different things. When you build toe sills, generally the key design criteria are the crest elevation of your toe, the elevation of this is sand backfill, this is rock. So we need to know how high we need to build our rock. We need to know how high we need to fill with sand between the existing shoreline up here and our toe sill structure. And then we need to define our different planting zones. So that's really kind of the rest of the design process was driven by answering those questions to take our concept design to a site-specific design. So we looked at some tide data, as Jesse mentioned. We were fortunate enough to have a USGS recording tide gauge, not too far from the site. It was a little bit, and these are wind-driven systems, so it's a little bit suspect, but you work with what you have. So we went through an analytical process and derived elevations for the common tidal benchmarks for this system. It's largely a wind-driven system, so that kind of, you know, that what you got going on up here at your gauge may be different than what you have going down at your project site because of the winds, because of this funnel-shaped estuary. But again, it was better than not having any data. In an ideal world, you can stick a tide gauge out there or a pressure transducer and let it sit for a month or two and get some very site-specific elevations. The other thing that we did was what's called a biobenchmark survey. So we were fortunate enough to have some folks from DNREC who took an RTK system out there and surveyed for us. We shot the elevations of different plant communities, and that's a really good surrogate for tidal datums, as well as it tells you more directly what elevations you should plant your plants at, because you know that plants are successfully growing on your site at those elevations. So in this case, we kind of overlaid the plant elevation data and the tide data, and they by and large corroborated each other. So that was nice. But you know, so I think if I only had to pick one of the two, I would definitely go with the biobenchmark survey, given the distance from the tide site. But if you've got the opportunity as part of your design process to look at both tides and the elevations of the species you're attempting to plant, those are really good way to kind of come at the same key elevations from two different ways and form a weight of evidence. So what we ended up doing is we took our mean high water elevation of about 1/2 foot. We decided that we wanted to go 1/2 foot above mean high water. So typical living shoreline designs will put the crest elevation anywhere at about mean high water, sometimes a little bit less than that, to maybe 6 inches or 12 inches above that. We wanted to build in some headroom so that we had greater longevity for this project, so that we could if we get some accretion in here, as sea level rises, we have the ability for this marsh to accrete a little bit more, and the toe will still hold that fill, and we'll get a little bit longer lifespan out of it. We also had a client and a landowner who didn't want to do the project more than once, and they opted for the greater protection of having that toe sill come a little bit above mean high water. We took some of the other design information and we used that to come up with this elevation here where the sand meets this, and then to define our different planting elevation ranges for both the low marsh and the high marsh zones. As I said, we did a survey. This is the detailed survey that Jesse referred to. You know, you might want to do it eventually. You don't need to do it in your initial phase, but when you go to detailed and final design, it's very helpful. That information was turned into site-specific topo maps and bathymetry. And then from that, we established a couple different cross-sections. I guess I'm getting ahead of myself. This is the plan form that we came up with the toe sills. We have gaps in here for hydrologic design. It's a series of segments that overlap, and if you notice, these western ends flare outward. And the intention behind that was to protect these openings from direct wave exposure and attack to the northeast, where we've got our strongest direction from our coastal storms. And the distance offshore was established basically trying to balance. We wanted about 20 feet of low marsh and 20 feet of high marsh to get our average slope was someplace around 20 to 1 in each of those zones. But it's a balancing act because you don't want to encroach too far offshore. I'll show some pictures in a second. We had rock line gaps to provide a little bit of protection in those openings. And then we established a fairly straightforward, simple planting plan based on the elevation range established for both the low marsh and the high marsh. And then without getting into any detail, there was a whole process to look at the design wave height and use that as the basis for sizing the rock. And then real quick in our last couple minutes, I don't want to take up our entire break. Looks like I am. You know, we translated the project onto the ground. We did that again using just simple RTK. So we were able to do it in-house, didn't need to call out a contractor. Staked out where our various sill segments were going to be, and then we were off to the races. First step is to put out some geotextile so that it provides a foundation for the rock so that rock doesn't settle down. Our bottom here was fairly, you can see people aren't sinking down. It's fairly firm sand with a thin layer of mud over top of it. But it's still a good idea to either have bedding stone or some geotextile to make sure that that rock doesn't sink down into the black ooze. The installation itself was pretty straightforward. Once we got the geocloth in place, you know, we loaded the rock into a dump truck. That dump truck backed down that earthen berm. They loaded it out with a long reach excavator. That excavator reached it out offshore, kind of loosely dumped it, piled it onto the geocloth inside of our PVC markers, and then moved it around mostly with the bucket, but the final touches were definitely moving rocks into place by hand to get as close to that trapezoidal cross section as we could. There's just a picture of a section of toe sill. Once the toe sill was installed, but none of the backfill had been put in place yet, and you can see one of the gaps right here. That gives you an idea of the offshore position. Same view here, just taken from some drone footage flown by one of the volunteers at Center for Inland Bays, which gave us some nice aerial shots. The backfill followed a pretty similar process, so our permit required that all the toe sills had to be constructed before we could backfill. Then we just took sand, dumped it in a dump truck, backed it down the berm, dumped it out, and graded it out with a bulldozer. That was a pretty straightforward process. I'll give a shout out. This was the Fish and Wildlife Services maintenance crew at a Little Creek who did all this work. So familiar with maintenance work around the water, but had not built a living shoreline before. So with the right kind of oversight and very skilled equipment operators, we were able to work together to get this to design. Here's just a quick shot once the backfill and the grading is complete. So you can, the original soil berm is along here. Now that's been built out about 20 to 30 feet, depending on where you are in behind these toe sills. Just another shot of it from the backside. You can see the gaps. You can start seeing the moisture line here as the sand's been inundated for a couple tidal cycles. I mentioned the rock line gaps. That was to allow tidal circulation between the sill segments. We ended up putting some smaller rock in here and create what engineers would call an invert at the elevation of mean low or low water. The intention here was to allow full drainage of the marsh channel or landward of the toe sill on a low tide. So the sand backfill hasn't been placed here yet. So now here you can see it, and then we put 2 rows of oyster shell in here just as an added backstop to help prevent migration of the sand out of that sill and to break up some of the wave energy that might sneak through that gap. Planting we did as a volunteer planting effort on the order of like 7,000 plants. We had, I don't know, 15 or 20 volunteers and pretty much banged out about 85% of it in a 3 or 4 hour work period one day last July. An aerial shot of the plants going in. I won't go through this in detail. You can see it in your materials, but you know, rock, sand, plants, and people are what put this living shoreline in the ground. Nothing terribly fancy. This is, you know, got some design behind it, but on the more simplistic side of living shorelines in that medium range that's not just plants, it's not just plants and coir logs, but you're starting to incorporate some hard material. So these last couple slides are just sort of a chronology. This is the site when we started, before the toe sills went in. Same view and all these, notice these trees up here. After the toe sills were put in, after the backfill was laid down, again, you can kind of see this wetting line as it's come through a couple cycles. These were these stakes here were the line between low marsh and high marsh transition, so that was a nice confirmation that we had our elevations about where we wanted them. This is the site the afternoon after it was planted, so July 9th, just a little over a year ago. 1 month later, still kind of hair club for men look here, but you're starting to see things green up. By 2 months later, really looking like a marsh. We were really impressed at how quickly the vegetation established on this site. Starting to go into seasonal senescence. This picture was significant because we had a coastal storm offshore. I don't have a bunch of photos that I'm showing today, but we had overtopping of this on a coastal wind event. So we did have some hydrologic connection to the impoundment in the back, but fortunately we did not have any erosion. And then finally, this was the site about a month ago. So this was after the first winter. We couldn't be more pleased with how the vegetation not only filled in the first season, but survived the winter and then continued to take off as soon as things got warm again. So that's the site about a year after installation. So that's all I have in terms of slides. I know we're gone way over our time, so I apologize for that. With that, Britt, I'll turn it back over to you.
Okay. Thank you, Brittany. My name is Allison Rogerson. I'm an environmental scientist with DNRAC, with the Watershed Assessment and Management section. And I know that we're in day 3. We have a great set of, you have had a great set of information coming toward you about biology, figuring out your site evaluation, your site situation, and just heard from Jesse about how to do that, and then from Chris about all the materials. So this is really, how do you put it all together? So you have all this information, your head is spinning, but you want to move forward to design your project. And so I'm going to be presenting on how to put the different pieces together and keeping in mind your project goal, since that is very important. So you've learned a lot about how living shorelines are just an interconnection of energetic conditions, your biological community components, your horizontal and vertical position of your shoreline, and they're all working in between each other. And you can design a living shoreline project to maximize all of those things, but it's also very important to keep in mind your landowner goals and legal limitations. You can dream up something, but it might not be realistic. So it's good to keep in mind these other factors as well. So living shoreline goals, you've heard about these already, even this morning. So primary goals that we really talk about for living shorelines in terms of what problems are you addressing. Habitat enhancement, Chris mentioned that can come from several different angles, trying to make the habitat better for different reasons. The biggest one is really shoreline position, and that's just a fancy way of saying erosion control. So you're going to be changing your shoreline position both vertically and horizontally, which is a good way to think of it. And then another primary goal may be water quality, and that comes in a lot of times if you have a project that is driven by a protected area or that has certain funding or is part of a bigger effort to improve a larger area. And then there are secondary goals like aesthetics and recreation or access that are also important. And I say secondary because you can't necessarily walk into permitting and proposal and say, this landowner wants to put in a living shoreline just because they think it's pretty. Well, as Chris mentioned, you need to be addressing an issue or a problem, and these secondary goals can be added on. Chris mentioned you don't need to have just one goal. You can definitely have a project that is designed to meet several goals at one time. So I'm going to run through some of these goals and how your goals may influence your design. And then I'm going to go through a case study, one that Jesse introduced you to, the living shore or the site down on the Lewis-Rehoboth Canal, and walk you through how we would design the project based on the information that we know. So thinking about living shorelines in two different categories, and this is based on DNREC's Shoreline Stabilization SAA. So you don't have to apply for a permit and go forth with a proposal based on these, but it's good to decide early on in your design which route are you going. So according to the SAA, you can think of the living shoreline as either conventional, so bio-based, or soft, and that would be comprised of native vegetation, sand fill, those Coir Logs that Chris just showed you, oyster shell bags. And then alternatively, you can go more the route of a hybrid living shoreline where it's a combination of hard and soft material. So you have all the components that are listed above, and then in addition, you would add on some other components like Oyster Castles, offshore, or wave attenuating devices in all the different forms, maybe some logs or an offshore tow or a sill with a marsh planted behind it. And it's also good to keep in mind to be in the living shoreline mind frame. And these are definitions that are taken again from the SAA, so that living shorelines, whatever you're designing, they're meeting your goals. And in the end, if you can answer yes to these questions, then you're on the right track. Is your design going to offer resilience to shorelines? That may be from wake, from storm surge, from waves, or even rising sea levels. Is it going to use predominantly natural materials or in combination with, man-made structures, but predominantly natural materials? And is it going to help sustain or enhance the ecological functions and the connection between upland and aquatic areas? So whatever you design, if you can answer these questions, and you are on the right track to having a viable living shoreline. So jumping into the goals. Habitat goal, you may come at this from the standpoint of wanting to create certain substrate or certain hydrologic conditions for certain species. So maybe you're in an area and you have shorebirds and horseshoe crabs. And so you want to make sure that when you design your living shoreline that you are still providing the right conditions for those. So, and that may be difficult. You don't really think of shorebirds migrating shorebirds in a living shoreline, but we have a site at the Indian River Marina where we knew we had horseshoe crabs. So we learned some lessons, but we learned that planting our native grasses in clumps was more effective than planting plugs, because the horseshoe crabs could come up and kind of bump and go around them instead of tearing them up. So designing for what species are using it. If you want to encourage shorebirds to come in, or wading birds to come in and feed there, you want to make sure that you're leaving your mud flats and your shallow areas. So maybe doing an offshore section, offshore protection, but then behind it keeping some open water areas and mud flats where they can come in and forage. Also, if it's important for you to allow fish and other nectins to be able to come in, you want to have access to that. So ensuring that you have tidal flow. So in the example that Chris just showed us at Sassafras, that offshore still wasn't continuous. It had breaks in it, and that was to allow water flow, and the access by fish and crabs was an important component of that. It's fish and wildlife property, so they wanted to make sure that they were providing habitat. So if that's one of your goals, then you can tweak your design to meet that need. And if you're just wanting, if you're coming at it from a habitat standpoint, looking at wetlands, it's important, as Chris mentioned, to make sure that you're selecting your plants based on what conditions are already there. If you're in a completely saline situation, you're picking Spartina alterniflora, we have, as you did at Sassafras, we did a project at the Blackbird Reserve that was really brackish, so we were picking arum and species that were native there. If you have like a really more of an even freshwater situation, as I have an example coming up the Delaware River, you're going to be looking at even lilies and other SAV. So it really depends on what conditions are already there that you're designing for what's appropriate. Now coming at it from, still looking at habitat, but from an energy situation. You know, you heard from Ashley last week about oysters and bivalves. If you want to be creating habitat for species like crabs and oysters and mussels or SAV, you want to be able to control the energy. You're coming at your design from an energy standpoint. You need to make sure you're creating the right conditions. So your design may look like the bottom right picture where you're stacking up, whether it's oyster castles or wads, offshore, and you can see the water line there. It's coming just above mean high water, so that behind it the energy has been reduced, and you're creating more calm and less turbid habitat that SAV can flourish. You're creating, you're using those wads or oyster castles as an area for oysters to land on, for spat to grow on, and encourage habitat creation there by controlling the energy. Now this is a complex example. I stole this from Josh Moody, who did this presentation last year. This is way up the Delaware River, across from Philadelphia, wraps around the Cooper River, spurs off right around Camden. So we're very high up. And this is a good example of designing a living shoreline for habitat where you're keeping biological diversity in mind. So there's a lot going on in here for sure. At the bottom of the page, you've got this landfill that's surrounded by forest. And then as you work to the top of the map, you get into more of the coastal. So there's sort of a cattail, boggy area. Then they're creating this flooded area that's dominated by Newfar, and then Coir Logs around that, and then they're leaving those brown tips that are between the Coir Log and the blue water. That's going to maintain mud flats. So then you have that added component there. Then you notice offshore they have some SAV that they wanted to protect and some freshwater mussels. So they've added these the gray triangles they've designed in there are to create more habitat, more retreat behind that for the SAV and the mussels to flourish. So the other component in here to notice is that coming from the upland towards the waters, there are a lot of natural water features trickling through. So that's really important when you go to design, that you make sure you're taking into account those natural drainage features and you're not blocking them. They will come back and they'll come back and bite you if you don't account for them. So this is a complex design, but it really takes into a lot of consideration the components that are there, working with them, but also creating habitat for a lot of different components, a lot of different types of species. Shoreline position, as I mentioned, is probably the most common goal for living shorelines, and usually addressing the energy is a big component for that. So if you're having offshore waves coming in, if you're having boat wake, storm surge, addressing the energy is going to be really important for you to create the situation that you want, to make improvements to reaching your goal. So keeping in mind that the example here on the left, where this wave height reduction of up to 50% when the reefs are at mean high water level. So you can see on the outside of that picture, you see this angry storm wave energy coming in, and it hits this offshore oyster reef, and then inland of that, the water is much calmer. So you can come at this from a couple different ways. If you want to design your living shoreline for oysters, you're going to create maybe some oyster castles that are down low, and you're going to let the oysters build on top of that towards high water so that you have that right intertidal zone. Or if you want to design your living shoreline to really just attack wave energy, you can build those oyster castles or even offshore wads up to mean high water, and you can let oysters grow on there and colonize on there, but you're taking care of the wave energy right from the beginning. Shoreline position in terms of extent is very important. So maybe you're not just saying, I want to stop erosion where it is. I want to get a little more aggressive and actually replace what was already lost. So in this picture, you know, we've designed this living shoreline. This is at the Indian River Marina, where wetland had been lost and the edge was vulnerable. We're actually building out the extent of the shoreline by providing different tiers and elevation of coir logs that are protected by oyster shell bags. And then also keeping in mind for shoreline position that hydrologic connectivity. So Chris mentioned this just a little bit, but you know, taking into consideration very carefully in living shorelines, your water levels and where your materials are placed. Chris mentioned how very carefully they place those rocks to meet mean high water and planning for those storm surges. You know, he had pictures of where the water came in that fall storm, making sure that you understand that certain areas are going to be flooded at certain times of the year. And then water quality is the final primary goal, looking at the filtration capacity of what's there. So, you know, how many mussels, how many oysters do you have? How much water can they clear in a certain amount of time? You know, how many particles are suspended in the water column there? How long do they have? How much area do they have? You can really calculate out how much filtration capacity is possible. So if that is something that's important, as was for the Miss Pillion project and in other areas, depending on your funding or your goal, water quality can be one of your main goals that you're going to design. So if you have oysters that are already in existence, as they did in Miss Pillion, you want to be sure to use materials in a design that are going to encourage more colonization of oysters so that you can maximize that filtration capacity while also stabilizing your shoreline. Some of the secondary goals that I mentioned, recreation or access. So there was a living shoreline just put in Dewey. If it's important for a living shoreline to also allow for residents to come in and go swimming or wading, get into the water, then that's important that you allow those breaks. Maybe it's a neighborhood and they want to be able to have access for kayaking or for boating. You need to be able to provide breaks or protection. So incorporating those components into your design while you're also considering addressing your primary goals. Also, aesthetics. Chris mentioned this a little bit. If you're designing a living shoreline project that's going to be around a power plant, then it's not necessarily as important. But if you have a shoreline project that's going in somebody's backyard or along a river walk, as you see on the left, you want to make sure that it is attractive. So, and it's very possible to incorporate your primary goals in with aesthetics. We have a project being proposed for the Delaware Botanical Gardens in Dagsboro, and obviously at a botanical garden, aesthetics is going to be very important, and so that will feed into the materials that you use, thinking in advance into the future, how are these things going to look, but keeping in mind that compared to what's on the right here, that a living shoreline is naturally going to be more aesthetically pleasing. In addition to your main and your secondary goals, there are lots of important considerations that are certainly not meant to be overwhelming, but important to keep in mind, other than your landowner goals. So when you're designing your project, keeping in mind the parcel of land that you have and what is right next door from them. That's something you document in your site evaluation. Are there any structures? Does your landowner have a dock that you need to work around and make sure that you don't block boat access for, or some kind of ramp? Maybe you have a navigable channel that's nearby that you need to make sure that you account for, that you're not infringing into that navigable channel, and other safety considerations if you're putting offshore stills or wads or oyster castles, that you are marking them and thinking about boat access and normal boat traffic. And then are there other existing protected resources? Maybe there are oysters, SAV, or horseshoe crabs that come in there that you need to account for when you design your project. And then is there going to need to be mechanical shoreline access? So you may have a project that's great, but it requires an excavator or something to come in, but you have a lot of trees in the way. You know, that's going to make a big difference in your budget, and it's important to consider that. The Sassafras project, which is pictured here on the right, they were able to bring in machinery and dump trucks because there was that berm. They did lay down pallets to make sure that they weren't compacting and hurting any of the habitat there. So it's a consideration, it's not necessarily a limitation. Some other things to think about when you're designing and putting together your timeline is your construction, not only access, but the timing of that. Are there time of year restrictions that are related to wildlife? And the surrounding landscape, is there a steep slope that you're going to have to work around? How are you going to be able to get into the site? May influence things. Keeping in mind that nature-based features are not self-sustaining. You're going to need to be able to come back to this design after it's been installed and adaptively manage it. And Josh will talk about that just in a little while. A lot of these different limiting factors and considerations will make a difference in your costs, your budget, and depending on your funding, you may be able to dream up something really big to meet your goals, but keeping your funding and your available money in mind is very important. And then also, of course, you have to say that there are limitations based, on federal and state regulations. So being realistic about what you can do. And then a little simpler is just even the amount of sunlight is important. So at a site that may have everything going for it, but you want to put in Spartina and there are just tall trees overhanging it like you see on the right, that's probably not going to be as successful. So you need to take that into account as you design your shoreline. So looking at this from the big picture, getting started, how do things flow through? So you want to meet with your property owners, figure out what your site conditions are, set your goals, figure out what your timeline is so that you can determine your permits, develop a budget, develop a monitoring plan so that you can make sure that you're meeting your goals. You're designing your living shoreline to meet your goals. You have to have a monitoring plan to make sure that you can document you've met those goals. Attend a JPP meeting, which is a joint permitting process meeting, and we will talk more about that tomorrow. Get your permits, plan for construction, always leave time for monitoring so that you can adaptively manage. Any item on this list that has an asterisk next to it represents something that the Delaware Living Shoreline Committee has a helpful tool available to assist with. All right, I promised to walk through this process using a case study. So we're going to use, as Jesse already started to talk about this morning, using the Lewis Canal site and zooming in. We can see, and this is what Jesse mentioned, that there was a previous living shoreline project along the canal, and it just so happens that the proposed project that I'm going to mention now was our control site. So we were monitoring this control area as we monitored our living shoreline, and over the years, while we've seen our previous project succeed and be sustainable, we've watched this control area continue to erode away, and so we thought this would be a great example for us to walk through and make as sort of a mock project proposal. So zooming into that a little bit, you can see on the top of this picture the nice stable shoreline where our project was, and then the proposed project area, you can see that the shoreline is a little more jagged. It's definitely further back from the rest. Our project timeline is we've already started doing some baseline monitoring. We've been doing that for years, actually, which is unique in this case, and we've started to draft up some of our design right now. So if we were going forward with this fall, we would try to go to that joint permitting process meeting and come up with some final designs in the fall, and then in the winter, go for submit our permit applications and get supplies. Next spring is the best time, we feel, to install living shoreline. Install a first tier, sort of down low, to establish baseline elevation and continue to monitor that and monitor the accretion through the summer and then into the fall, be able to go in and add to that, adding a second line and then some interior Coir Logs, and then the following spring be able to plant inside of our new wetland and continue to monitor that, and then even into the next year, monitor the success of the project and adaptively manage. So kind of walking it through in a timeline of the order that we would go through. But looking at the conditions that we know about at this site. So we have documented erosion and cusping. Because we've been monitoring there for several years, we've been able to document that we have about 1/2 of a foot of erosion per year, which is the same that Chris was mentioning. It doesn't sound like a lot, but it does build up over time. We have some of our monitoring plots actually falling into the water. So you can see clumps of Spartina, calving off, falling into the water. And through our monitoring, you can see on this map the treatment site that's in green, nice stable shoreline. The yellow and the red dots are representing this proposed area, how the shoreline has retreated since 2014 to 2018. So we've been losing, we've lost 49 square meters in this one particular area. So this shoreline is about 115 feet long, and we've lost a significant amount just in the last 4 or 5 years. Some of the existing features that we want to take into account when we're designing this project, there is an abundance of oysters there. There are also a lot of rib mussels, so that will help hold into our Spartina and all of our plants. And then in the canal, we know that there are a lot of suspended sediments, and that's important because we know that when we create our empty cells, that over time with every tide cycle, this site will fill naturally, and we won't need to bring in fill. Looking at the neighboring shoreline, all of this information we got from our site evaluation. So we went out and went through that whole site eval process, and that documents a lot of things, including the neighboring shoreline. So to the north, we have the Coir Logs and the oyster shellbags from our previous project, but to the south, we have this higher elevation. There's some riprap, there's some concrete rubble that was put in place years ago, that's sort of relic, and that's important for us to know in terms of energy and what we need to tie into with this project. As I mentioned, navigable waters or channels may be important. In this case, the channel, the Lewis Rehoboth Canal, this is a map of the channel. The actual red line is the center line. We have the orange line is the edge of the channel, and then the green line represents sort of a buffer they put around that. And when you're designing, you can't go inside of that line. So we have to take that into consideration because we are pretty close to that line. So that would influence our design if we wanted to put anything offshore like Oyster Castles. We would probably be infringing on that buffer, and that would be a problem. So we need to make sure to account for that when we design. Also looking at our upland features, so we know that we have a little bit of low marsh left, but that as we get to high marsh, it's dominated by Iva and Phragmites, so we don't want to create any kind of habitat where frag can easily colonize. You can also see in the picture on the left that due to all of the erosion that there is a steep drop-off, and there's a sharp edge there that we need to account for building up to so we can reach our optimal height for Spartina to grow. So putting all that together, we know that our shoreline, our goal is for shoreline position. We want to stop the erosion. We want to build the wetland out vertically, out horizontally, and up vertically, and encourage the oysters that are there, encourage more recruitment. We know that we have low energy. The fetch we determined was only about 360 feet, so very short fetch. Although we do know that there's a lot of boat traffic on this canal, and so there can be a lot of wake. And we know from experience that there can be some winter ice, so we want to take that into account. We've had some damage in the past. The slope is mostly low. We do have some very steep cutting banks due to erosion already. So looking at what we need for bringing the shoreline position up. In terms of a vertical lift, we need a total of about almost a meter, just under a meter of lift, because we know that our eroded banks, the elevation is -0.4. This is all in NAVD 88. We know our shoreline edge from going out to survey it, and we know the elevation of Phragmites. So we want to be below that for sure, but we want to make up the difference between the eroded banks up to the healthy shoreline edge. And then we want to account for a few inches or a few centimeters for sea level rise, just as we did at the Sassafras project, so that this project can be sustainable into the future. And we know that we want to build this project out horizontally so that we can replace the wetlands that have been lost. That's about 3 meters out. And the length of it, as I said, is about 115 feet. So the wave energy here is not very high. We have some features. We have lots of sunlight. We want to stay out of the channel and avoid those oyster beds. So taking all of that into account, throwing this into, this is an aerial view. So we have, you can see the north arrow. We've got the Living Shoreline project to the left and the riprap rubble to the right. What we've designed for this project is a winding shoreline edge that will account for the offshore oyster beds, and also be able to build up from the shoreline edge all the way to what's left of the existing Spartina, reaching that elevation. And so because it is a fairly big drop, we created not one but two sort of shoreline edges. So this is all with oyster shell bags. We opted for oyster shell bags in this design because we know about the wake energy that can be in here. And as Chris mentioned, Coir Logs can break down over a series of years, and we want to make sure that this project is more sustainable. Also, by having the oyster shell bags, we're providing even more habitat for the oysters that are there to colonize and extend even further and maximize on that opportunity to secure the sediment and allow this to sustain. So we have the two. We would install this first outer layer of shell bag, allow it to fill in until the fall behind it with the sediment that we know is suspended in the water column, and then come in the next in the fall, and add that second layer of shell bag further in and allow it to fill up even further. So that will allow us to sort of have a tiered project design where it steps up, and so we're able to meet the optimal elevation that we're looking for. Now looking at that, and then I'm sorry, I also wanted to mention that to encourage sediment accretion and give the project some stability, we wanted to install Coir Logs perpendicular to the project internally as well, kind of creating these smaller cells for the sediment to settle down in. This is our overhead view. Looking at the profile view, which is also important to provide, you can see how this lines up with the mean high water line, the mean low water line. Starting with the mean low water line over on the right lower, you can see we've got that first tier of oyster shell bags that are going to be right there in that intertidal zone, and then letting sediment fill in. We had that second single row of oyster shell bags, and then the Coir log that comes in behind it that will meet up with the existing shoreline edge, and then allowing this new marsh platform to fill in with native plants. Keeping in mind that we want this to be sustainable, so building it up to a slightly higher elevation in the future. So there's that timeline again, going in that first spring, building in the first layer, and then adding to that in the future, always monitoring so that we can make sure that we're meeting our goals of building up the elevation, creating a marsh platform, and adaptively managing if anything comes along based on experience. Here, we know that there can be some loss of plants. The sediment accretes very quickly here, which is very fortunate. It sort of builds itself, and the project that we've already done was very successful. We had some winter ice damage that we had to come in and replace, so coming back and looking at it over time and making sure that it's still healthy, and making sure that you're meeting your goals. All right, that was a quick version. Do we have any questions that rolled in?
Okay. Okay, well, thanks, Brittany. Thanks to all the other presenters today. I love being on these webinars and at these meetings, and especially at this training, because, you know, no matter how long you do this kind of work, and I by no means have been doing it very long, maybe 10-ish years, but you always learn something new, or you're always reminded of something. You know, this is such a growing field. There's new things happening all the time. There's new innovation. There's new projects, and it's so easy to miss things or to forget about things. And I think these kinds of meetings and webinars are just absolutely great because, like I said, no matter how long you've been doing it, it's always great to get a refresher and learn something new that you've never seen before. So I appreciate being asked to be here because it gives me that sort of scheduled excuse to get a refresher course as well. So my name's Josh Moody. I'm the Restoration Programs Manager at the Partnership for the Delaware Estuary. We're one of 28 national estuary programs, and as such, we're a clean water organization. We get a little bit of our money through the EPA's Clean Water Act. So for us, living shorelines are really, you know, have a very strong nexus to clean waters. You know, we talk about all the different ecological benefits of marshes and also of shellfish that make a lot of the fringe and their home on the offshore locations of them. So in my role as Restoration Program Manager, I work in a variety of different habitat-related projects, including our Living Shorelines program, which it began around 2008, and we've been involved in a variety of different projects with a ton of different partners in Delaware, New Jersey, and PA since then. So we play a lot of different roles in them, but in addition to designing and installing living shorelines, you know, one of our PD's primary focuses is monitoring. You know, a lot of us in the organization have scientific backgrounds, and monitoring to us is really key. I mean, how do we know that our project is actually functioning as a living shoreline? Where's the life? You know, and how do we know it's meeting its goals, as Allison spoke about, we'll touch again on in just a little bit. But additionally, monitoring can also help us, you know, identify potential problems before they happen, you know, for adaptive management. You know, living shorelines, they're like gardens. You know, that's the analogy that's commonly put out there. And as such, you know, they're going to need to be tended. You're going to want to keep an eye on them. And you want to get in front of issues before they arise, because sometimes they're not necessarily visible until they get out of hand. And once something gets out of hand, you know, it's a little bit harder to rein back in. So in today's talk, I kind of want to combine all those different subjects and give like an overview of, you know, what living shoreline monitoring tends to look like and how that feeds into and plays back with maintenance and troubleshooting. So, you know, the idea with monitoring, like I said, the goal of it is my living shoreline meeting its goal? You know, how do we know that this is doing what we want it to do? Now, as was touched upon in a couple of other talks, Delaware Living Shorelines Committee has put together a living shorelines monitoring framework, a goal-based one, as Allison spoke about. And the goals that she mentioned are the goals that are highlighted in this framework. And what this framework does is, for each of these different goals, it's going to give you a series of tables that provide you with relevant metrics and a variety of appropriate methods that you can apply to track progress on your living shoreline. So I'm going to talk about that today, and then I'll provide a quick example of its application at one of our living shoreline sites. And then with maintenance and troubleshooting, you know, maintenance and troubleshooting is one of those, you know, strange topics to do in a talk, but it really does come off of monitoring fairly well. So in that section, I'm going to present just some of the common sources of issues that can arise and what types of issues they may be. You know, what sort of material troubleshooting might you need to do? What about that, you know, the interaction between elevation, sediment trapping, vegetation, which has been mentioned a few times today and I'm sure on other days. Drainage, Allison just spoke about that. It's a huge one. I'm going to provide an example of one of our longest projects that, you know, it's been on the ground 10 years, but it hasn't just been sitting there by itself. You know, it's been an interactive process with it. So I'm going to lead you through some of the different adaptive management and the maintenance and the troubleshooting that we've done there since 2010. And then at the end, since I know you guys are getting these packets or these talks, I've provided some reference tables where it lists a variety of different issues and what you can sort of look at if you're seeing a particular item. So I'll just do a quick run through of those, and then you'll have them for your own personal reference. So again, the foundation of monitoring is my installation performing as a living shoreline? And the wording of that's a little specific because, you know, a living shoreline, you know, as was touched on by Jess this morning, there's a lot of different definitions of them, but from PDE's point of view, and what seems to be stated in the SAA as well, is it's not a pile of materials in a place. I mean, you can take a wheelbarrow full of grass and you can throw it on a shoreline, and is that a living shoreline because it's grass? Not really. It's really how is it functioning? Is it performing? You know, living is an adjective. It can be used as a verb, and we want this shoreline to be doing that. And so we want to know about that. So really what this simple model kind of shows you is, you know, how we move through this process. You know, we've got this problem, and because we have identified a problem, we have an associated goal, you know, in the first step. And then we're going to take some structural materials and put them down. Living shorelines are not natural. They are engineered processes that contain a lot of natural material. Those materials are going to interact with the physical environment and the biological community, which again are going to feed back to each other and change this physical state as well as the biological state, which is going to feed back to each other again and provide a bunch of different outcomes and changes. And it's right here where these arrows are moving around in a circle here where monitoring comes in. Are we documenting those changes, and are they on a trajectory? And importantly, are they providing that ecological uplift that's required for something to be a living shoreline? So we're really in like a then versus now kind of situation, which is, you know, that's what monitoring is there to address. So that's really the only way to evaluate the effect and the performance of the materials on the landscape. But it can do that in a variety of ways, and it can set you up with a variety of different strengths. So standardized monitoring, the reason it's really sought after recently, and not just by practitioners, but also by, you know, people in a variety of different roles in the public sector, from regulatory to policy. You know, if they want to put policy or regulatory items in place, they want to make sure that these rules or these suggestions they put out there have the greatest likelihood to succeed. So bringing this information there can help us identify different tactic selections. You know, even if you're just monitoring for yourself, other people may find that interesting and it may be good. You know, I've got a site, it used to look like your site. What did you do? Did it work? No, well, I'm not doing that. I'm going to do something else. So this tactic selection, you know, in meeting different goals. The project design and the expectations, you know, for, you know, if you have a pile of materials at a site, you can construct them in a whole bunch of different ways. You know, which configurations are really working and how long does it take them to work? You know, if we install something today, you know, what is it going to be next week? Is it going to be working 2 years from now? Is it going to be meeting its goals? So setting these expectations, adaptive management, getting in there in front of these problems. And again, people don't always like to talk about it, which is why I put in, you know, this talk talking about a site where we did a lot of adaptive management. Negative data are good data. Things that don't work, it's very important to talk about because it helps other people move forward. And we all know with negativity bias, it does not take much for a design, a type, a process to get a bad name. But it takes a lot for something to develop a good name. So information sharing and, you know, all of us working together towards building the best type of projects to meet their goals is very important, and negative data are very helpful for that. So, you know, as Jesse mentioned with the site evaluation document, this is another document that was put together by the Delaware Living Shorelines Committee to help people figure out how to monitor their shoreline. Okay, great, you know, I'm putting this stuff in, but what can I do to, you know, track these different changing levels of function? You know, maybe I'm not a scientist. I mean, how hard is this going to be? You know, where do I begin? How do I organize information? And this is a document I think that we're all very proud of. There was a huge group of people who worked on this over a long period of time. And, you know, it's not a very long document, which is nice. So it gets to the point, and to make a nice streamlined document like that was a big effort of a lot of people. And it had multi-sector input, you know, practitioners from the public and the private sector, the regulatory professionals were involved, academic professionals, you know, thinking about how we're going to make recommendations that are consistent with things people have seen in the past. So really what it does is it does three things. You know, it's going to provide guidance for you first off. You know, it's going to ID the necessary items to evaluate if your living shoreline is meeting its goals. So it's going to help you develop project-specific objectives from your predefined goals. And I definitely want to mention that this document's not going to tell you if you have this type of project, well, then you have this type of goal. It's going to assume that you've already identified a problem, you've already put a project together, and you probably have a goal. Now, based on that goal, it's going to help you develop these objectives, and it's aligned with SMART objectives. It's going to help you then, it's going to take you to a series of tables based on your predefined goal that's going to help you select which metrics are important to you to help you understand if your project is meeting its goal. And then for each one of those metrics, it's going to recommend a variety of methods. And these methods, you know, some of them will be high rigor, high end, you know, sometimes either very tough or expensive ones, but we always like to put in what we call a Home Depot method. Now, it's amazing what you can learn with a measuring tape and a PVC post. People learn lots of stuff with just that, and we try to include those in there because this is not an exclusionary document. This is a document that's for everyone. And it's going to help everyone facilitate a structured monitoring plan. Because it's nice, you know, when you have a document that will suggest how you do things, but it's easy for our minds and our desks to get cluttered up. And so how do we organize that information in a way that's going to make us able and want to use it? And once we want to use it and we do use it, you know, it'll help us, you know, view those changes. So it's going to take our objectives, our metrics, and it's going to, you know, help us think about how we're going to look at it. It's going to help us track the progress over time and develop a monitoring timeline for ourselves with little boxes you can check. But it's also going to provide a full template for a full monitoring plan. Maybe you need to develop an entire monitoring plan, you know, from start to finish. So a template will be provided there. It'll walk you through all the different things that you need to think about, help you list out your objectives. But maybe you work for an agency and you already have a template you have to deal with. So it also just provides a series of tables that you could take out and you can just put into your own monitoring plan template. So what we're going to do, and then starting on the next slide, is I'm going to walk you through what this document looks like and how it's used, talk more about the metrics and the method. But a lot of times, that's sort of jumping the gun a little bit. People might say, well wait a minute, what am I even looking to compare? You know I want to see these effects here, but how do I even really know that they're because of the things that I did? So, you know, these slides are a little wordy, but I know that you were getting the presentation, so I wanted to keep them in there for you. And although these, you know, possible monitoring strategies, you know, can seem complicated, they're really not. And it's really two ways that you can mentally organize the way that you want to look at these. You can just simply be looking at a before and after for your project. You know, I want to collect information on these specific things before I do it and after I do it. And am I seeing the changes that I desired over time? Now, you can do statistics on them, and if you wanted to, if you're from a discipline that does that, it's really a one-way and over a pair of t-test sort of way to look at it. But it really answers the question, is how do we know the changes, how do we know that the changes that we are seeing would not have occurred anyway? You know, that's one of the things where you have to start getting a little more complicated in your design, because we're seeing the changes, but I wonder if we're seeing them somewhere else where we didn't do anything. And that's where the design expands a little bit in the number two, the before-after control impact. And all that means is you're looking at the place you did your thing on your living shoreline and a place near it that's like it that you didn't do anything, and you're looking at the same things at both places before you install and after. So then you can start to ask the questions, well, are the changes that I'm seeing over time different on my living shoreline than on my area where I didn't do anything? And if so, that can imply a difference due to the installation you did, assuming everything else is equal. And one of the tough parts with that is controls in a natural setting, a scientific control. I don't really believe they actually exist in nature. You can have adjacent areas that are similar in a lot of conditions, but you'll definitely want to take a second to see what could be different between those two sites and could have an effect. But even though they're not perfect, there are ways to think about how you're assessing those changes, just over time or just over time compared to a site where nothing was done. So getting into the framework just a little bit, we talked a little bit before about, you're going to come into this document. When you turn it over, open the cover, page 1, you've already kind of got a goal in mind. You've done your site assessment. You know a little bit about your site. You understand that there's a problem there that you want to do something about, and you have a goal. And Allison mentioned those 3 goals that this document deals with earlier. Shoreline position, which is, our fancy way to say erosion control. There's changes in habitat. You might want to see some habitat uplift or some water quality uplift. And so for each one of those goals, it provides you with a couple of tables. And in those tables, and there's an example of the shoreline position one here, you'll see across this row, if you can see my pointer, there's different metrics and associated methods, user considerations, which will help you choose your methods, but there's also a couple different classes here, core metrics and conditional metrics. So one thing I should mention is the group that put this together didn't just, throw darts at a wall covered in metrics that people have used and put them together in here. There was a lot of different, workshops. There was a lot of in-person, phone call, email surveys with practitioners up and down the East Coast, in the Gulf, people that we know, people that we didn't know. What are the different metrics people are using that they have found to be informative? So the metrics described here, these are ones that are commonly used. And what's nice about using metrics that are commonly used is when you talk to somebody else who's done something like you, if these are commonly used metrics, they might be looking at it in the same way. So this sort of helps with that sharing of data. But we split up the different metrics for each one into 2 different categories, that core and those conditional ones. Now, core metrics, in quotes, are the ones, that we say are required, that are essential to evaluate. What that means is that those metrics, no matter what type of living shoreline you're doing to meet that goal, these metrics are always applicable to that goal. So for example, in shoreline position, the second one down here is this horizontal position, the horizontal position of your marsh edge. Well, if shoreline position is your goal, the position, its horizontal position, is always going to be relevant. But then there's conditional metrics, and these can be project specific, depending on what your goals are, depending on what your shoreline looks like, what sort of habitat it's in, you know, and really what you're trying to accomplish there. You know, so some living shorelines, a lot of them, you know, are going to have vegetation components. Well, if you're doing a living shoreline that actually doesn't, you probably don't need to put any metrics in that look at vegetation components, right? But some could also be user-specific. There might be certain types of metrics that are just by nature of what they are, just tough to wave energy, height, or amplitude. You know, those can be a little tougher, and maybe that's something as a user that, you know, you don't feel that you have the expertise or the way, you know, to do. Some might also be more costly than others. Now, we tried to put in a variety of different, you know, considerations, cost considerations, different methods that have different costs, that have different technical expertises. But, you know, some things are just expensive to do. And so these conditional metrics, you know, you may rule them out because they're not relevant to your project, you don't have the ability, the equipment, or the expertise to look at them, or you just don't have the cash on hand to do it. So the metric is really the thing we're looking at, and the method here is how we're going to do it. So for horizontal position, this core metric here, you know, you could look at it, you could do some surveying, you could do some GIS, you could look at it with LiDAR, surveying equipment. On all of those, if you look over here, they're all common ways people do it, but they all require some expertise. But, you know, here's our, like I said, our Home Depot one, our suited for all user groups. And we tried to make sure that there was one in there, because another important thing we want to, you know, highlight is that money to monitor is not always very common. And sometimes engaging citizen science groups to do this can be very helpful. And we've tested a lot of these different methods with different citizen science groups monitoring shorelines in New Jersey. The ones that are in here, you know, all tend to be fairly easy to do. So for all user groups, distance from a permanent post or other structure. This is your PVC and a measuring tape. Put a marker in the marsh, little landward of the shoreline, one out in the water, put a tape between them, and keep measuring where the shoreline is along that tape. That provides great information. Do it at a few spots along the shoreline. Just because, you know, you're not using a $40,000 piece of equipment to do it doesn't mean it's not valuable. So we tried to include those types of methodologies where we could for each type of metric. So here we've looked at this, a horizontal position of the shoreline, you know, for here, you know, a lot of cost and expertise, a little suited for all user groups. If we want to look at some of our habitat ones, these are all some conditional ones. You know, depending on what sort of target species you're looking at, what sort of habitat you're dealing with, you may want to look at things in a different way. And we tried to put a variety of different methods in here that cover those different types. You know, you could have biomass can cover a lot of different things. It can cover different types of animals. It can cover vegetation. Percent cover is a nice, easy way to gauge the amount of vegetation that's there, or the number of animals, fiddler crab burrows, rib mussel lip count. You can look at lists of species at the site. You can count the number of oysters. Those are all things that are suited for a variety of different user groups. And some of these ones that have some technical expertise involved, or some cost things to consider, you know, those might be things that if you have a certain type of expertise in, or, you know, I don't know, your neighbor's a retired biologist and they're looking to get out and do something. Some of these things, you know, can be overcome fairly easy, but we try to list them in those considerations just so there's things to consider. So something like morphometrics, looking at the length of fish or oysters, you know, it can be costly because it's very time intensive to go out and do that kind of thing. But if you're using a citizen science group of people who are retired, that may eliminate a variety of those considerations. So those considerations aren't there to be statically prohibited, but they're just things to consider. And depending on who's doing this work and how they're doing it, they may not be an impediment to you. And then, so the next thing after the tables, you have selected your metrics, you've selected the methods that you're going to do. Now you're going to get a series of 3 tables here. And the first one's going to help you really organize your whole project. And it basically follows this line of thinking. What do we want? How are we going to measure it? When and where are we going to do it? How are we going to evaluate it? So here we have in this table, and you can have as many rows as you like, you set your goal. Within the document, as you go through it, you'll set some objectives that are aligned with, SMART objectives that a lot of different agencies, like to develop monitoring plans with. So for my goal here of shoreline position, my objective is the vegetated edge moves waterward from the original position. I did not say how far, anything will do. But this is where you just state what you want. Here's its associated metric, and here's how we're going to do it. You list out the methods that you chose, you decide when you want to do that, and where you're going to do it. So say I'm going to do this distance from a permanent marker. I'm just going to take my site, I'm going to split it into thirds, and I'm going to put a transect down the middle and then put one at the 75th and the 25th percent distance from the starting point. 3 equally spaced transects. Then my question, now it's called analysis question, but it doesn't have to be, it's not really complicated. My question is just, did the horizontal position of the marsh change and in what direction? I'm basically just asking the question based on my objective. And how am I going to do it? I'm going to look at the average change in the positions per year. So on these 3 transects, every year, I'm going to measure along that tape where that marsh is. I'm going to take an average of the 3, and each year, I'm going to see if it's moving towards the water or if it's moving towards the land. So this just helps you organize your thoughts. Here is structurally how I am going to do that. And now, up here, you've talked about when you're going to do it. I'm going to do it 2 times a year. I'm going to do it 1 time a year. I'm going to do it after peak vegetation growth. I'm going to do it, until it gets too cold and I refuse to go out anymore. And that, so we'll give you a time tracking table. Set up your time tracking table, what I'm going to measure, how I'm going to do it, when I'm going to do it, and you can just cross these things out. This is great, if people are moving in and out of agencies and in and out of groups. It's a great way to just organize when these processes happen, who did them, what they did, when they did it. And then a progress tracking table. So again, this has a little bit from the first table, my goal, my objective, my metric, my analysis question. Now I have my baseline. Maybe you conducted an as-built survey because it changed a little bit. Maybe you went out, you built an edge, and you went out and planted grass. Well, if you went out and planted grass, are you going to say your living shoreline grew that grass, or did you actually plant it? So maybe your baseline condition and your as-built condition differ a little bit. And then you just start tracking. What did you measure, in after build 1? And what's that change? What did I measure in after build 2? What's that change? And so now you can start just by looking at these to see that change per metric over time. Again, a great way to just track things that doesn't have to be very complicated. So I'll quickly run through an example of our Mississippian living shoreline. This is the DuPont Nature Center at Mississippian Harbor. Delaware Bay's out here. This is the Mississippian, and this is Cedar Creek that comes up here. The Denrec boat ramp right up here. Salt marsh was eroding, but also the home of one of Delaware's few, but there are a few, and there's becoming more, low intertidal oyster reef. Well, the Nature Center, this had been eroding for quite some time, but they were also really interested in expanding this reef. It had been expanding for a little while, and then it just hit a spot where they were worried that maybe it was retracting or it just wasn't moving upriver anymore, and they just wanted to see if they could grow it because they thought it was a very nice feature. So in April 2014, we went in and we took 3 areas of this shoreline and we did some shell bag and Coir Log installations there. We left a few spots open so we could track differences in, in changes on places that were treated and places that weren't. Actually, last year in 2019, these treatments did so well, we actually went in and filled these areas in using a similar technique. And then down here, as you know, we installed a variety of different oyster castle pods to try to make that reef grow. And as Chris said, there is a time and a place to use everything. And this is the time and a place for oyster castles because, you know, we had the existing population there. We know that if we gave them something, there's a chance they may grow. But oyster castles also break down over time. I mean, I don't think you want to use them for erosion control unless you want to install them again in, you know, X many years. But if you're building a reef and you think you're going to get some good set, you know, these could be pretty good. So the idea with these castles is we wanted to build up the population. As the castles start to deteriorate and fall apart, hopefully the oysters are now, you know, aggregating enough to build their reef. And we did that up around the shoreline too, hoping that at some point, you know, a nice reef would help fill some sediment behind it. And the goals here were shoreline position and water quality. So shoreline position, I'm going to move through these quick, and I'm not going to talk about every metric. You know, if anyone wants to follow up, we have some reports on this I'm happy to share. But our objective was to stem erosion. You know, we were going to, our horizontal position of the vegetated edge, we tracked it with an RTK once a year, at 1 meter intervals, and then we looked at it using the digital shoreline analysis software from USGS. You can do the same thing with AMBER and ARM. So what did we see over time? Okay, so on the x-axis we have time, spring and fall 2014, spring and fall 2015, 2016, 17, 18, 19. Right here, the 0 position on the y-axis is the position when we start. So negative includes landward movement, positive is waterward movement. Our control site is in the dark blue, and our nature center treatment area, our living shoreline, is in the blue. So we installed in spring 2014, but it wasn't really more than a year afterwards. You know, we tried planting some veg. It didn't hold too well, but we're tracking the vegetated edge here. So we had the materials in place, but it really took a bit over a year, actually until 2016 when we went out there, that we saw that natural veg really move up to where we had put those materials in. So we're actually even seeing some of it retreat. And it makes sense. I mean, these are plants. You're not going to put something in. They're not going to, you know, slap each other on the back and think it's great and all run out there. It's going to take some time. You have to grow rhizomes. You're going to have to, you know, start moving across this. So this was nice showing us. It was a little nerve-wracking in here in the second year. We didn't see much going on. But we hit our elevation targets, and by, you know, 2 years into it, that veg just moved out naturally on its own, and it has held its position since then. Water quality. At PDE, you know, we're really a shellfish organization. A lot of us have a background in shellfish, but, you know, how do we know that we're getting a water quality uplift? And what we're really looking at is if we can increase the shellfish population and we know how much water they filter, we can say they're pulling this much more stuff out of the water just through their feeding activity. So how do we do that? Well, what we wanted to do is we wanted to count the different amounts of shellfish out there over time, take some measurements of them, and then we wanted to take the information we know about how much they eat and apply that to the population so we can estimate what they're doing. So what do we see? Again, we have number of animals here and dates on the X. We looked at oysters and mussels, and over time, well, we got more animals. Great, but what's important is this is their size classes. Size is on the x-axis, percent of total on the y, different years in the boxes. Whole bunch of little animals in the first couple years. That makes sense. Little animals don't do a whole lot. They don't eat much. Once we start getting into 2016, right, when we start to see that vegetation success, we start to see this, the population start to take a more normal shape. That's great, because bigger animals are the workhorses. Some are going to get older and they're going to die off. You got young ones to move in. This normal distribution tells us something nice about that shoreline. We take that distribution of size classes and the counts, we turn it into a change in biomass. How much tissue have we grown on that shoreline over time? And we translate it to filtration. So just like with the vegetation, our first couple of years, we weren't seeing too much filtration. This is just the amount of stuff they're pulling out. This is the amount of it that's particulate nitrogen. But again, you know, is it a living shoreline here? The grass hasn't moved. Not really filtering anything. Is it functioning as a living shoreline? You know, we didn't know. But by 2016, after a little time, you know, give the ecology time to grow, we start to see that growth. And now we can say, well, the living shoreline is meeting its goals. The shoreline has been stabilized for a period of time. The vegetation has moved out to the edge of our treatment. And we have increased water quality there because these shellfish are eating and growing. So by that nature alone, they're pulling particulate nitrogen out, which can be considered a pollutant here. So this living shoreline is functioning as a living shoreline. We continue to monitor it. To date, like I said, we've expanded it, and it is, you know, one of the places that, you know, we are very interested in continuing to track over time because it provides a variety of different data types. If people are interested in it, we have a couple reports on it, and there's a whole bunch of other metrics that we did that I'm not going to, you know, put everyone to sleep right before lunch with. I think we'll just keep moving through it, and we're going to go into maintenance and troubleshooting, right? So, so I'm really just going to discuss some of the major sources of the issues that you can run into on a living shoreline. But, you know, in general, these issues, they're either usually sourced from installation miscalculations. You didn't install something to the right level. You blocked some water, or maybe unexpected changes in these feedbacks here. So, you know, really when you're talking about maintenance and troubleshooting, you're either going to start altering structural materials, or you're maybe going to let some biology go or try to facilitate some biology or something in a place where it wasn't before. So we're really focused on this part of the model here with maintenance and troubleshooting. And I'm going to try to stick to a couple of broad categories here, but anyone can email me, you know, with questions on that. So materials. So this is the foundational stability of a living shoreline. Every living shoreline is engineered, and you're probably putting something on the ground somewhere. So that's creating the conditions for life. So the structural integrity of the materials is important. Are you putting the right thing in the right place? You know, Chris talked about this, you know, at length, so I'm not going to spend too much time on it. You know, there's certain things that are good in low energy environments, certain things that are good in higher energy environments. One thing I would like to say is there's, you know, position appropriateness as well. It's not that often, unless it's in a very low environment, where you see a living shoreline that's really just like one type of thing. I mean, we did a lot of, you know, Coir Log and shell bag living shorelines for a while, but if you're really trying to create a mosaic of habitats, you might be using different things in different places. And different materials, like Chris stated, have their strengths, even if it's not structural integrity strength. Coir Logs, for example. You know, you're in a more energetic environment. You do not really want a Coir Log to be your primary energetic defense. But if you are building a complex marsh terrace that you want to, you know, you want to build up different elevations in different places so you can put different types of plants, create habitat complexity, I love burying Coir Logs. Bury them in the ground. You know, you have something else as your energetic defense. Use these Coir Logs like Allison showed in her design to create this topographic complexity. They'll break down a little bit. Roots can grow through them. But even when they break down underground, we've dug out some logs that we've had down there for 7 years. They don't completely break down. They would not survive in the front of a treatment. But once they're buried, you know, if they're in anoxic conditions, they're still going to be providing that sort of topographic complexity. So different things might be position appropriate. There's seasonal considerations. I mean, in this one picture, you can see some ice on our Oyster Castles that held up, but that doesn't always happen. Vulnerability to ice is something we have to deal with here, and if you're interested in that, I suggest reaching out to people who work in the Great Lakes region. These are people that are very familiar with dealing with ice. And Great Lakes, which are basically act like oceans because of their size and their conditions. But vulnerability of ice is a big one. We want to use sacrificial materials, you know, that are less costly, that may be destroyed, to protect the materials that we really need to keep in place. But are you in a site that has seasonal docks? You know, so you may feel protected in the summers, but in the winter when they take them out, you know, you're going to get the increase in energy, and you're going to get, you know, ice coming in. So when you think about that protection when you're doing your site evaluation, you know, as Jesse was talking about earlier, you know, think about seasonality too, where there's things that are in place in one season that may not be in a place in the other. You know, it'd be great if someone put docks in the water in winter to protect it from ice and took them out in the summer, but, you know, they don't do that. Biological interaction. They can be good or they can be bad. You know, Chris talked about shellfish earlier. You know, you put out oyster shell bags. If they get completely encrusted in shellfish, oysters especially that cement together, you can get a pretty durable structure. But as Allison talked about, you know, there can be negative interactions, and it's not, be careful the way you word this, it's not negative because of the interaction, it's negative into the effect that it could have on the living shoreline. This is where Allison had commented on, you know, sparse planting, providing pathways for horseshoe crabs to move up and in and around the material. Also, if you know, we had Coir Logs in the front here, you know, those, the crabs don't look, they're not big, but, you know, their legs are sharp, and you get a lot of them coming up here, and they'll tear certain materials apart. So you want to think about what's using it. We did a living shoreline with Stevens Institute in Atlantic City where we literally built a horseshoe crab walkway because of their ecology and because of the fact that they follow a declining elevation when they move out, you know, from the sand back out into deeper water. We literally built them a ramp. And so far, they had seemed to be using it, but they weren't seeing too many traps up in there. They were seeing them come in there. Elevation and sedimentation. Now, I'm going to come at this from the perspective that most living shorelines are going to incorporate some sort of vegetation aspect. You know, so for a living shoreline, a vegetative living shoreline to grow and persist, it's going to need to grow vertically, you know, to adapt to sea level rise, and, you know, trapping sediment is going to do that, and plants play a big role in this, but they're extremely sensitive to their position in the tidal datum, which is, I'm sure, been discussed in this workshop already. So I'm going to discuss plants sort of in the context of elevation and sedimentation as well. And so, you know, during the design phase, you're going to be targeting a specific elevation, and you're probably going to choose that elevation based on plant choice. But plants can grow within ranges of elevation too. And so if you're working on, you're just using a salt marsh example, you know, you plant too low, you know, you're going to get really stunted vegetation because spartina needs to be exposed for a certain part of the day, and it really does best between mean water and mean high water. But depending on your tidal datum, that can be pretty good, you know, a pretty big range. So when they're planted lower in the datum, they tend to grow taller. You know, they have to, you know, they want to get more air down in the soil, aerate the roots. When they are planted a bit higher, they tend to grow a little bit shorter because now they're putting a little bit more energy into below ground biomass. They don't have to grow up as much. They need to bring things in and stabilize themselves with their roots. So you have a little idea, you know, thinking about sea level rise, thinking about how much, you know, sediment you want to trap. Sometimes it's nice to kind of split the difference in here. Because if you can get those plants in their dense, you know, they're going to trap more sediment, you're going to help the marsh grow, and it's going to help keep your plants at a good position. You know, here's just an example of this. These two treatments, this was 2010. This is Matt's Landing. You can see this one right here on the other side of the dock. Put them at the same time. We thought we tracked them to the same elevation, but this one compacted. The sediment sunk a little bit more. It was 4 inches below mean water. This was 2 inches above, and this is a couple of months after planting, and you can see a huge difference. I mean, it doesn't have to be much of a difference to see a real effect. But a lot of times you want to get sediment before you plant, right? So sediment trapping, if you're not going to bring it in, if you're not going to bring in fill, you know, if you're working down in the inland bays where the TSS in the water column is kind of low, you know, you may want to bring some sediment in there. You don't wait 30 years to trap sediment. But working in places like along the Lewis-Rehoboth Canal, the Delaware Bay, sediment-rich places, but just because it's there doesn't mean it's easy to get, especially if you have fast-moving water. You know, the water doesn't want to let go of it. And so one of the things we found is this, you know, disruption. Disruption is key. This is that Lewis living shoreline and this initial shoreline. What we wanted to do is, you know, build up to a certain level. So what we ended up doing is installing some baffling. You can see some of that here too as well behind a shoreline in Mississippian down in at the Mississippian living shoreline. you know, once water starts hitting the dropping sediment out, you can start to see how along these castles you start to build up these little areas of sedimentation around those. And then once you start planting those, you know, that's going to cause further disruption, positive feedback loop, you know, sedimentation and disruption is going to feed more sedimentation and disruption. This was fall 2014, and by spring 2015, that disruption has helped us a lot. We were able to trap a good bit of sediment here. So disruption is a good one for that. Drainage. Allison touched on this as well. You know, you just don't want to trap water in a living shoreline. You know, cooling water is going to lower oxygen. If you've got plants there, you know, it's going to completely prevent root development. Everything's likely going to die off. So if you are seeing water back there, you may want to develop your own drainage. Another way that you can actually help bring oxygen into a living shoreline that might be holding water, that seems to have good drainage, but it just might be kind of soupy, is if you use older plants, they have wider columns, they can bring more oxygen to the ground, and there's been a couple of studies done that if you, plant plants in clusters, use dense vegetation, taller vegetation in that as well. I love what Chris showed with those larger plant mats being rolled out. Great example of that. You know, they're going to bring more oxygen down in the sediment. They're just physically able to. So, you know, your placement of your materials to let water out. This is a DEM that we did of a living shoreline we have in Nantuxet. These red and yellow areas indicate more low-lying areas. So as you'll notice, as we did our design, this is the water out here. This is a road back here, and water from the upland would be flowing out this way. What we tried to do is follow those paths, leave space here. You know, water's going to come down here, move into that, move out there, create these drainage pathways. You may want to fortify them. I think that was brought up earlier too in the Sassafras landing design, because, you know, where you have moving water takes things with it. So you can either allow for these natural drainage pathways, or you can create some creeks. But however you do it, actually this is an example of one here where there was a crab shedding barn behind the installation. So there's literally a pipe shooting water out like 2 years after we installed this, maybe actually even more, probably like 4. And so what did we do? Well, we built a creek. We stabilized it with shell, provided the drainage pathway. Drainage is very important to look at, as Allison mentioned earlier. So in these last couple of slides, and I think I'm on track to wrap it up here in a few minutes, I'm going to look at our mass landing adaptive management. This is just adaptive management from 2010 through 2016. We haven't done anything since 2016, but we are going to do something in 2020 as well. So it'll have been 4 years since our last intervention, so to speak. So these were just, this is 2010, very simple bio-based living shoreline. There's floating docks out here, pretty low energy environment, you know, put in some Coir Logs to build some terracing, add some shell in front of them. This is the one actually right here when I showed a couple slides back, we didn't meet our elevation target. It's right down here. This is the one that you know, we did stay at our elevation target. 2011, post-Irene and Lee, everything doing well. 2012, post-Sandy, everything still doing well. And 2016, here's those crab shedding barns. That's where they ended up putting those in. Still a pretty decent living shoreline. This was all kind of rip-rap just back to the frag. That's all that was there in 2010, as you can see right here up in this picture. So what happened there? All sorts of things happened there. So in 2010, I showed that picture of the physical elevation. We had a physical elevation problem. Elevation was low on that one treatment. We had to add a second deck of logs. Okay, not too bad. You know, took an afternoon, get away from the desk a little bit. Everything good till 2014. Yep, and then we go. Now we got creeks, I say creeks form. They form from the blasting pipe. But they were there. So we got 6 new logs and a bunch of shell to help stabilize those creeks. Still not a big deal, not bad. We haven't done much in 4 years. 2015, though, is where, you know, 5 years after install, Chris had mentioned this earlier, we started to lose logs, icing. Started to take them out, and in 2016, we lost a few more. At that point, we just replaced the Coir Logs with shell bags. The shell bags have been great since then. We put them at the same places, put them to the same elevations, and, you know, everything has been stable since then. A couple new creeks are forming in one. from some changes in the upland causing changes in drainage, which we're going to address this year. But, you know, that's where this monitoring really comes in handy, right? You know, you can, first you can go out there and see what's happening and know that you're going to need to do something or that something was taken away. But by tracking this over time and the position of, you can say, all right, well, we lost 4 logs in 2015. We lost a couple more logs. It's in the same place. You know, maybe we got a tactic problem here. What are we going to do? Do this every few years? Maybe it's time that we switch this up. We switched it up. So we learned some lessons through it. You know, compression affected the elevation in 2010. We learned the shell provided the best edge protection at this site. But the Coir built and sustained internal elevation. I touched on that before, and I included a graph here for it. Plot 3 is, we usually establish plots waterward up into the high marsh, you know, running perpendicularly from the shoreline. This plot 3, this was up in the living shoreline, in the treatment area. It wasn't out front of it, it wasn't down front of it, it was kind of up high in it. And we had a paired control and an impact, that's our living shoreline here. This red line indicates mean water, right? And our y-axis here is our vegetation robustness. Oh, no, I'm sorry, this is our elevation on this line. Cut that off here. And then the black bars are 2010 and 2016. So this is that two-way and over this before-after control impact. So before, in 2010, our control and impact area for this place where we were building the living shoreline, they were generally at the same elevation. But by 2016, that kept scouring away, eroding away there, and that's getting lower. Our elevation was getting lower. But in our living shoreline, the elevation, we brought it up and we kept it up. This mean water line, remember, that's like the lower threshold for our target vegetation. So we've been able to maintain position above it. And these internal Coir logs sort of help us do that, help provide the structure by burying them in there. Also, this is our edge movement here between our treatment and our control in this table down here. Negative is erosion, positive is moving waterward. And so our net movement was waterward in the treatment, continued erosion in the control, and, you know, our associated losses of area. So these last two slides, I'm not necessarily going to go through them, but you've got them for yourself. You know, they go through these material, different types of issues. So your materials are deteriorating from energy. So maybe it's a structural material change like I just talked about. Maybe you want to put out attenuation devices. So it'll give you a couple of different scenarios and tell you a couple different things to look at. Plant's not growing well. Check the elevation. Check for water retention. Check your time frame. I mean, how long has it been? I mean, if it's only been 6 months, maybe they shouldn't even be growing yet. Maybe you shouldn't sweat it so much just yet. If you're only using plugs, you can try something else. So it touches on a few of these different ones and helps you think about a few things that you could look at. So, but I do want to bring back the goal-based framework summary, because this is a really helpful device. I mean, I find it helpful. I use it. We're going to start plans for a new living shoreline. I'm going to go out with the site evaluation guide, and I'm going to go out with this, and that's how we're going to develop our materials for our permit application. So it guides the user in identifying the objectives, the relevant metrics, and the appropriate methods. It's going to help you organize all that in a few different tables, and it's going to help you produce that monitoring plan that not only helps you organize your thoughts, but again, if you're in an organization where new people may come and go, it's nice to have a place where everything is, you know, organized and kept. So if we have time for questions, I'll take a couple. If not, you know, anyone, you can just email me. Obviously, I'm not at my desk, but I'm pretty good with email. So just shoot me a line, and I'll be happy to get back to you.